Mountain Time until the other break at 1:45 p.m. Mountain Time, and then we have also in the afternoon, we start with the Paleoclimate Advanced Webinar Series with 2 talks, one by Matt Osman and the second by Emily Jude. I also want to remind you about that we all observe our code of conduct, which is shown here on the right. The talks should be typically 20 minutes and 5 minutes for discussion. So we give you a warning after 8 minutes, so 2-minute warnings. If speakers have questions, you find on your reaction buttons the raise hand in the lower menu. If you're done with your question, please lower your hand so that we know that you have done. We will follow the chat question, so we have a limited time, and so please continue any discussion in the chat session. We are recording and live on YouTube, and we also encourage that you submit your slides afterwards to Elizabeth Faircloth. Elizabeth sent a link to you where you can then upload the slides. So the first talk will start then at 10:05. So we have a couple of minutes until we start. Maybe Esther, you can already put up your slides, and we start that at 10:05.
Yep. Okay, new share. Share. Okay. How are we looking?
Very good. It looks great.
Okay. Okay. Yeah, I think I should wait a couple minutes.
We have 2 minutes. Yeah, 2 minutes.
Anyone have any quick question about logistics while we're waiting? Out of the way.
Okay, let's get started. Our first speaker is Esther BRADY, Paleoclimate Working Group activity. So updates from the Paleoclimate Working Group activity. So go ahead, Esther.
Thank you, Arnie. As Arnie said, my name's Esther BRADY. I'm a project scientist at NCAR and co-chair of this working group. I'd like to also acknowledge me, my co-chair, as well as the other NCAR Paleo leads, Betty Otto-Bleesner and Jean Ju, for their important contributions to the activities of the working group, as well as many others who you will see contribute to our making our activities successful here. Okay, so first I'd like to list what our working group science priorities are and the themes that guide and drive our activities. I presented a lot of these slides recently to the co-chairs, and so of the other working groups and this was kind of a way of introducing them to what we do in our working group. First, seek to engage the paleo data community for their expertise in paleoclimate observational data essential to evaluating our model simulations and gain a greater process understanding in that partnership. Second, we seek to increase the capability to model paleoclimates. Our working group has tested lower cost, faster versions of the CESM2 for paleoclimate applications. We use, for example, the lower resolution 2-degree atmosphere model coupled to the 1-degree ocean, and that can achieve about 50 simulation years per day on Cheyenne, our supercomputer now, with a relatively low cost in CPU hours per simulation year. This makes it a workhorse for long simulations of interest. Our working group also spearheads the use of water and carbon trace for improved proxy comparisons and process studies. But moving forward, we'd like to foster the use of high resolution capabilities for our community, which will open up new science applications, such as studying the impact of background climate state on weather phenomena and for improved proxy model comparisons. Another high priority is targeting past to future applications. This will help inform future climate change. For example, combining simulations of out-of-sample paleoclimates with paleo data to inform climate sensitivity, to investigate past tipping points in the climate system. Lastly, we seek to use the latest models to advance paleoclimate science to perform grand challenge simulations and push our science forward, such as using multi-millennial transient simulations with coupled interactive dynamic ice sheets, dynamic vegetation, which isn't quite yet, we hope for the future, biogeochemistry and carbon cycling, such as occurred on glacial to interglacial timescales. We also push for using the whole atmosphere model and high resolution coupled paleoclimate simulations. So first, I just want to bring to your attention that these CMIP6 PMIP4 simulations that were performed with the CESM2 are available for your use and documented in publications listed here. The simulations are all available on the NCAR Climate Data Gateway. We have the PMIP4, the CMIP6 PMIP4 Tier 1 simulations performed with the CESM2 at the 1-degree nominal resolution for the mid-Holocene, the last interglacial at 127 Ka, and the mid-Pliocene available and documented, as well as the PLIOMIP2 simulations with the CESM2 and also our older versions of the CESM that you can find at this link here. These are published in the AGU special issue for the CESM2. Ran Feng led a James paper on the Pliocene work. Betty Otto-Bleesner led a paper documenting the CESM2 mid-Holocene and last interglacial simulations. And Jean has documented his work simulating the glacial, last glacial maximum in a paper in GRL. There's also a special issue in climates of past for core, in which our simulation has been contributed to many papers, and Betty's also led a paper there comparing the models, all the models for the last interglacial simulation. Next, I'd like to let you know about some of our recently completed projects. First, we have the transient last interglacial simulation, which was a project that we worked on with the land ice working group. This is a joint project. Simulation time was from both of these working groups. This was a project to simulate the evolving Greenland ice sheet performed with the CESM2 coupled to the dynamic ice sheet model CESM2 in collaboration. Well, yeah. The Greenland ice sheet evolved in response to orbitally driven insolation, as well as changing vegetation input simulated by Biome 4 run offline. A paper documenting this is now out, led by Aaliyah Summers, and simulation output is currently being released on the Climate Data Gateway. And you can find some of this output at these links here. The second project is the development of the paleo-calibrated version of the CESM2, a project led by Zhang Zhu in collaboration with members of AMP and other atmospheric model working group members. The project is motivated by finding that the high ECS of CESM2 simulated a very unrealistically cold glacial cooling, and Jean talked more about that yesterday in his talk. This CESM2 with the high ECS prevents many paleo applications for very out of sample climate states. After testing microphysical parameterizations, Jean found better agreement with paleo data with some small modifications and got a more consistent LGM cooling with these modifications. The paleo-calibrated version also performs well for the historical period, as shown in the picture on the right. His paper in James has been accepted now, and a tag of the code will be released, as will output from the simulations on the Climate Data Gateway. The next slide presents some ongoing work that we currently have, that we're currently working on. First two projects use CESM2 coupled to the WACM atmosphere component. And these are performed in collaboration with members of ACOM. The simulations are now starting to be documented. First, Zhang has completed the simulations of the LGM with this version and the pre-industrial. You talked about that yesterday. These paleo-calibrated mods have been included in this version, and we saw his interesting results yesterday. We have at least two papers analyzing and documenting the CMIP6 past 1000 simulation in the works. One paper will document the CESM2 simulation, focusing on the ocean response to volcanic emissions. This will be led by NCAR CGD and ACOM scientists. The other paper will be led by UK researchers to compare the responses between the UK ESM and CESM2 past 1000 simulations compared to reconstructions from tree ring proxies. As illustration, these figures show the response in CESM2 to the largest eruption over the last millennium, Somalis, that occurred in 1257 CE. Another ongoing project is our simulation with the Heinrich Stadial 11 event using the lower cost 2-degree CAM atmosphere component with the 1-degree ocean. Here, a 0.2 spheroidal meltwater flux is applied to the subpolar region of the North Atlantic for an idealized forcing of this event. The motivation is to investigate the capability of CESM2 to simulate a abrupt events in response to tipping points in the climate system as compared to the records. Plots show the state after about 2,000 years of the simulation, which is now out about 4,000 years. This event is suggested to be important to the collapse of the West Antarctic ice sheet during the last interglacial period. The meltwater input leads to a strong reduction in AMOC that you can see on the left, very strong bipolar seesaw pattern here in the center, and warming at depth around Antarctica. An NSF project with collaborators from the University of Washington will use the simulation and CESM to explore under what climatic conditions lead to a collapse of the West Antarctic ice sheet. So there's past to future implications here. We're now about 8 months away from the end of our current CSL allocation and have very ambitious plans for the remaining time. And I mean computer time as well as people time. First are 2 joint projects with the Land Ice Working Group that were proposed by members of the external members of the working group. The first will simulate the evolution of the Greenland ice sheet through the Holocene, starting at about 9,000 years ago with transient orbital and greenhouse gas forcing. The simulation will have vegetation data sets updated from Biome 4 runoff line and the Northern Hemisphere residual ice sheet updated periodically from ICE 6G data sets with the Greenland ice sheet evolving using CESM. The simulation will test the capability to simulate Greenland ice sheets, rapid retreat and regrowth over the Holocene period. The second project will investigate the glacial inception of Northern Hemisphere ice sheets with the CESM2 Simulations, starting from the end of the transient last interglacial simulation with transient orbital and greenhouse gas forcings. An extended CESM grid will be used to cover the Northern Hemisphere domain and this was used to show glacial inception with conditions fixed at 116,000 years ago, led by Marcus Loverstrom et al., and it's now been accepted for Nature Geoscience. The last simulations we hope to complete in year 2 are listed here with our CSL allocation. First, Jean, in collaboration with members of AIM, plans to conduct a paleoclimate perturbed parameter ensemble study to explore parameter space in the atmosphere model with a focus on the ability to simulate a range of very out of sample past extreme climate states. This will help constrain model physical parameters using data constraints and improve understanding of cloud feedback processes under different out of sample climate states. Another simulation at very early stages is the early Eocene hothouse climate, simulated using the CESM2 Wacom 6 middle atmosphere version. And Jean mentioned this at the end of his talk yesterday. This will be a great complement to his existing LGM simulation. And these will provide a really nice set of experiments with the whole atmosphere model component coupled to the rest of the CESM components. Lastly, we have plans to simulate the LGM using an early development version of the CESM3 coupled to their new ocean component, which is from MOM6. This, we hope, will be performed and set up in collaboration with the Ocean Model Working Group. We hope this will help shake out any potential setup issues we have. So we'll get started with the new development of the new developments as they go forth over the next year. It will also provide an early estimate of the equilibrium climate sensitivity of the developing CESM3 and test these new developments against the best glacial reconstruction. Next, we have some very exciting news to share. We just heard yesterday that our NCAR Accelerated Scientific Discovery Project called PaleoWeather has just been approved. This project involves a team from NCAR, led by Betty Otto-Bliesner, and the universities of Arizona and Connecticut, with Jess Tierney and Andrew Walters, Ren Fung, Clay Tabor, and Mary Grace Albright. The NCAR group will include me, Jean Zhu, CJ Sun, a postdoc, and Jesse Nussbaumer, who was the who's in CSEG. The project is to use the high resolution version of CESM3, which is was used with the IHES project on the new supercomputer coming to NCAR, and that's called derecho. We will perform 4 coupled paleoclimate simulations at the resolution of 1/4 degree in the atmosphere and land, coupled to 1/10 of a degree ocean and sea ice components. This will allow investigations of the dependence of weather phenomena on background state, and also investigate extremes and comparisons to proxy data at the high resolution. So we're very excited to get this going, but derecho is not here yet. So Betty will take some questions later, hopefully, if we get some time for questions after my talk. But this is just very exciting news we just heard. So this slide, I just want to let you know that we're in the process of revamping our Paleoclimate Working Group webpage, which is linked here. We hope, how am I doing on time, Arnie? We hope to be able to find more information, or you should be able to find more information about our working group here, our activities, and any resources available. We hope to get it updated very soon and have it more helpful for you. On it, we'll list recent and notable simulations, completed projects with landing pages with more information on how to find the output, how the model was set up, how you may want to run a branch or sensitivity off of the simulation. We'd also like to highlight any university simulations, point to any simulations run with CESM, done by the external community. We have links to some modeling resources on the GitHub repositories, and we can link any contributions from others that might have some cool tools out there in the GitHub. And there are links to current and former CSL proposals that you can read about what simulations are planned and what have been done. One important mechanism for greater engagement is our new Paleoclimate Advances webinar series. This link here takes you to the webpage that is shown here in the center. You can learn more about PAWS. It's sponsored by our working group, but steered by a committee listed over here, with early career scientists, both NCAR and at universities. And the steering committee is charged with developing themes for the webinar and inviting speakers. You can join a Google group on this webpage and also nominate speakers. And get the flyer for the current Paleo webinar that will be at 2 p.m. Mountain Time today, with Jess Tierney and Emily Judd speaking about their work reconstructing long-term temperature reconstructions from models and proxy data. So we're very excited to get this going, finally, get it off the ground, and we look forward to lots of engagement in the community and advertisement for our activities. Okay, this is a slide that I presented to the co-chairs that lists some of our identified needs, and we want to hear more from you about what you feel are the priorities for our needs going forward. First, we would like to make sure we have a low-cost, fast version to enable long spin-ups and transient runs. We want to maintain and keep and push high resolution, global and regionally refined grids for paleo applications. We want to push for geotracer capabilities in the new model, particularly carbon and water isotopes in all components. And there's, in order to spin up these passive tracers, we want to have a turnkey implementation of Keith Lindsay's Newton-Krylov fast spin up. A dynamic patient model would be great for future CESM. This will enable a richer set of impacts and feedbacks, and in terms of allowing simulations such as the Green Sahara and vegetation climate ice sheet feedbacks that we demonstrated in the last interglacial transient simulation. We also want to ensure that the model components can be extended for paleoclimate. So we want to keep the ability to have no anthro setup conditions and support for different topographies and continental configurations. We also would like to make sure we update our tools for the setup, analysis and post-processing, and particularly for the runoff model, as that's changing, and that has been difficult to extend to paleoclimates in the past with different topography and coastlines. Also, we'd like to make sure we can have good tools that help us create new grids for these new model components, such as the ocean model MOM, which has a tripole grid. And that's really it. We see the way forward here as identifying and supporting the community needs. We want to hear from you about what you think new simulations should be that we'll be developing for the new CSL proposal that we'll be writing in the latter half of this year after the workshop in the summer. This proposal will start November 1st. But we'd like to talk about ways we can get some greater community engagement. And I think the Paleo webinar is a really great start for that, but we'd like to understand and hear from you what you think might be additional ways we can bring in external members of the working group and get involved in our activities. Because at ENCO, we don't have in this working group a science or software liaison currently. We'd like to get one, but we currently don't have one. We're a small group of 3 people. You can see here, Betty is the leader of our group. And then myself and Jean are both project scientists. And we leverage work on our activities by collaborating with other members of other working groups and members of our polar and paleoclimate section at CGD. But we would like to get the community more involved in paleoclimate activity. And thank you. I'll take questions. Did I?
Okay, thank you, Esther, for the extensive overview. Unfortunately, we have only 1 minute left, so we have only one short question.
Okay. I see one. Oh, that's a clap from Greta. Okay.
The one question. So I may have a quick question if there's none. So the tripole with a MOM, I know historically the tripole grid had some instability or created numerical wave. Has that been improved compared to the previous pop version?
I haven't heard about any tripole grid instabilities. Are you talking about in MOM? I mean,
yeah, MOM.
Yeah. Well, the high res model has a 1/10 of a degree tripole grid. And that has been run for the pre-industrial simulation for like 500 years. And I haven't caught wind of any talk about an instability using POP anyway with the tripole grid in that configuration. So
okay, thank you. I think we need to move on. So if there are more questions, please go to the chat. So the next speaker is Jesse Valle-Vito, an ESL compatible model for the younger dryas.
Okay, great. I'll just let's see if I can share screen here. No, that's not quite what I want. 1 second, having a bit of a Zoom is not letting me necessarily share. It's giving me a whiteboard, but can you guys see my screen right now?
I see only a white. Just
a whiteboard.
Yeah.
Okay, I'm unsure why it's not giving me the option to show my actual screen.
So normally there's a shared desktop assigned. Maybe you can try that.
It's straight up just not giving me any options other than it's always something like this. Yeah, I was testing this out before and it was working. I don't know if it's an issue on Zoom's side.
I'm looking to see if I didn't do something.
Just a question, because I spend my life troubleshooting Zoom, but is it showing blank screens when you try to share?
When I click share screen, it's supposed to give me options for share screen, whiteboard, and other things, but all it's showing right now in the tray is whiteboard. There's no other options for how to share.
Yeah, if you recently updated Zoom, you might need a computer restart before sharing works properly.
Okay, I don't think I've
Jesse, I've just made you a co-host, so let's see if the button appears when I change your status in the meeting.
Shall we flip the speakers? Maybe a good idea. So you have more time, Jesse, to figure that out, to restart your computer.
I might be able to start a Zoom, like click out of here and start a Zoom with Jesse to test.
I sent the slides to one of my co-authors who's in the room. So if they can comment and just go through them. Sorry about all the troubles here.
That's okay.
Jesse, did you send it to me yet?
Yeah, I just sent it on Slack.
Okay, I got it. All right, let me just get this thing. Okay. Okay, let me share screen then.
Okay, go ahead. Yeah, we see it.
Okay.
Okay.
Right.
So sorry about that, all. So What I'm presenting on today is an ESL or eustatic sea level compatible model for the Younger Dryas. This is work that I've done with Deepak, who has so kindly come to my rescue for sharing the slides, as well as Dick Peltier at University of Toronto. Next slide. So a brief overview of what we're going to talk about. I'm going to go through kind of an introduction, present some of the background for what it is that we're trying to model and why it matters. Then go on and talk about kind of the nitty-gritty model parameters that we use to achieve what we did, talk about some results, and then talk about where we're going with this work, because it's still ongoing as we keep moving forward, and we're still running simulations. Next slide. So the Younger Dryas, which I'm sure everyone is familiar with, it was a rapid return to glacial conditions. It occurred about 13,000 years ago, lasted about 1,300. There's some debate on exact start times, exact end times. It's known to have been caused by a release of fresh water from proglacial lakes on the Laurentide into the ocean through the Mackenzie River Delta into the Arctic Ocean, which then would make its way out of the Arctic Ocean to the sites of North Atlantic deepwater formation, which would cause an AMOC slowdown. At least that's the current model. And on the right here, we have a picture of the Dryas octopetala, which is what the Younger Dryas is named after. I figured it should be, we should keep in mind that it's actually the pollen from these flowers that first led us to be aware of the Younger Dryas more than 100 years ago now. And so the kind of relevant part here is that the AMOC is slowed down or shut down or decreased for about 1,000 years. And that's what we're trying to reproduce. Next slide. So it's not like we're the first to try and model the Younger Dryas. People have been doing this for quite a long time. A recent paper by Love et al. Summarized a number of prior modeling attempts using CESM and other models. They identified 3 key areas of improvement, notably forcing strength, forcing location, and boundary conditions. And the reasons for these are that many models tend to apply a very strong degree of forcing over the North Atlantic with LGM boundary conditions. So our goal was to try and address each of these problems in turn. Try to find a way of reducing the forcing strength so that we're not adding 10 meters of sea level over 1,000 years, which is not justifiable from sea level records. Apply the forcing where we know that it entered the ocean, and move towards a 13,000 year set of boundary conditions, including things like trace gases, orography, so that we can argue that we're actually modeling the Younger Dryas as it would have occurred, not something completely different occurring at LGM. And so the reason for this is that LGM boundary conditions deviate significantly from those at Younger Dryas time. There's a lot less terrestrial ice. The trace gases and insulation are changed, and sea levels are somewhat higher, and ice coverage is just generally more limited. So we were trying to address these kind of failings of previous models and what we're doing here to accurately model the Younger Dryas. Next slide. So in terms of the location and duration information that we're using here, Kaigun et al. 2018 found 2 ice rafted debris layers in the Beaufort Sea, one at 14.5 thousand years ago, and one that's much weaker and later associated with the Younger Dryas. And so what's interesting here is that they found some evidence of a light forcing of about 800 years preceding the Younger Dryas, which we know was an outburst flood. And so this paints the picture of kind of a long, slow leak of fresh water into the Arctic Ocean, followed by a rapid, much higher degree of forcing. And so that's one of the tests that we ran here to try and see what effect that has. Yes, not much more I want to say on this slide. Next slide. So in terms of figuring out the kind of volume and flow rate, so how much water can we use How quickly is it justifiably entering the ocean? We made use of Tarasov and Pelche that argued that the peak flow rate couldn't be much more than about 0.2 Sverdrups. I believe their exact figure was something like 0.226 or something along those lines. And that's what we're using to constrain flow rate. I don't believe we don't use anything stronger than 0.2 at any point. So that gives us kind of our peak flow rate. In terms of how much total volume of water we can rely on, we're using the Barbados sea level record to constrain it to approximately, it can't be much more than 5 meters. And what should be kept in mind is that this 5 meter figure is obviously going to include all RSL contributions from every ice sheet that's deglaciating at that time. So that's going to include some melt from remnants of the Barents Sea ice sheet, the Fennoscandian, the Laurentide. So we didn't want to get close to 5 meters. We wanted to keep it a fair amount less than that. But I'll talk a bit in future slides about some ideas we had about how we can potentially get higher flow, more volume entering the ocean without an according sea level rise. So plotted on this, just back one sec. Just a bit more about this figure. Plotted on here is in the blue crosses, or the blue inverted T's, I should say, are the coral records from Barbados. The ones with short error bars are Acropora palmata, which are the ones that we used to kind of get our 5 meter upper bound here. The black line is the ICE 7G and Avium 7 predicted sea level at Barbados. And in red is the Walbrook isotopic record. So the red square here bounds what's happening during the Younger Dryas, roughly speaking, 12.8 to 11.7 is what the box is here. And so you can see there's really not too much sea level rise occurring, which makes sense because it's colder in the northern hemisphere, so you'd expect glacial melt to have slowed down. Next slide. So for model parameters that we use CESM 1.0. We had constant background and diapycnal diffusivity. Tidal mixing and overtides are turned off. I'll talk a little bit about why that could potentially matter. For orbital parameters, trace gases, orography, and bathymetry are all set to 13 Ka. And the one caveat here is that our land sea map is left at LGM because we spent quite a long time trying to troubleshoot and get it to work at 13 Ka with no real success. So what we decided on as a compromise was to put the main changes that occur between LGM and Younger Dryas in terms of land sea map in this area is the deglaciation of the Barents Sea. So what we did is we treated that as land of essentially zero height above the ocean. In terms of other decisions we made, we decided to keep the Bering Strait closed. I know that there is some argument about whether or not the Bering Strait was overtopped before or after the Younger Dryas onset, but we decided to keep it closed in the simulation. And then we integrated for about 2,300 years until the AMOC was stable. And we then started at that point to introduce forcing. Next slide. So we tried out 3 different forcing models. One where the freshwater is only entered in over the Beaufort Gyre, which is where we expect the water that caused the Younger Dryas to have entered the ocean. One only over the North Atlantic. This was primarily to test to what extent this issue of where you apply forcing actually matters. And then the third one was over the Beaufort, but with contribution from the North Atlantic margins of Northern Hemisphere ice sheets. And the reason for this choice was that even under glacial conditions, it's not unreasonable to think that some amount of fresh water is still entering the ocean. It's just that it's not a net deglaciation, right? And so that fresh water might still conceivably be applying a forcing without applying an according increase in sea level. So we wanted to examine that possible effect, as well as I mentioned with the Kaigwin results, try to see to what extent having a long, slow beginning to the Younger Dryas might change what's going on. In terms of forcing length, we either apply forcing for 100 years for the strong forcing tests, or 1,000 years for the weak forcing tests, and we find two different behaviors. And the strength of forcing is going to vary between 0.05 surge reps all the way up to 0.2. Now, not all, we didn't test this problem space exhaustively, but we think that the tests that we have done are going to provide pretty good ideas about what the effect of these different parameters are. Next slide, please. So this is all of our forcings on one slide. I will, of course, in the following slides, break this down into different sections and talk about those specifically. But what we have here is, as I mentioned, our spin up, where we let the AMOC to stabilize. We then apply forcing. The two black bars there show the duration of the 100-year forcing. We can see two different types of effects here. One effect is either the AMOC shuts down and stays shut down, or the AMOC recovers immediately once forcing is removed, because for the upper half of those tests, the forcing was for 1,000 years. And I'll talk about that a bit more when we get to that slide. But I think the other very important feature here is in the two strongest forcing cases that we integrated all the way through recovery, which are 0.05 and 0.12, which are the dotted red line and the magenta line underneath it. You can see that there's a very sharp increase in the AMOC upon recovery, kind of an overshoot of the overturning strength, which is also associated with stronger warming in the northern hemisphere and other regions. So that's an interesting feature that we're hoping to explore more. The other thing that's interesting here is that once the AMOC is shut down, it doesn't seem to matter too much how exactly it got shut down. Its recovery proceeds almost identically, depending on whether, if you see like the 0.15 and the 0.2 forcing, both spontaneously recover at almost precisely the same time, about 1,000 years after forcing is removed. Next slide, please. So this is a close-up of the strong forcings that we've done. Now, one of the ones added on here that I haven't mentioned yet is this 0.125. So that one is still under, we're still working on that one. It's integrating right now. The reason why we're doing that one is to try and zero in on what the behavior of the AMOC is when the forcing applied is very close to the threshold that's required to collapse. So we're trying to zero in on what that is. So here we have the 0.15 and the 0.2 in red and magenta this time. And the first of the black line is when we apply forcing. The second black line is when we remove it. And you can see that the AMOC actually keeps decreasing after you remove forcing, which leads us to believe that after a certain point, the AMOC is in its death throes and it's going to collapse regardless of additional forcing applied. So it's possible that we could, rather than do 100 years, we could move it to 75 or 80 or however much. But the question is to what extent that's necessary. As you can see in the legend, we've already driven down the eustatic sea level rise associated with these forcing events to the 1 to 2 meter range, which is much more reasonable than a number of other attempts to cause the Younger Dryas. Next slide, please. So here we have the lighter forcing runs. And what's interesting about these is that they don't actually collapse the Atlantic, the AMOC. What they do is just depress it. And so in both these cases, the minute that forcing is removed, in this case at 1,000 years, we see an immediate recovery of the AMOC. And what you notice here is that even though these are forcings are comparatively lighter to the ones that I talked about before, because they're occurring over an order of magnitude more time, the associated eustatic sea level rise is incompatible with the 5 meter limit in the 0.1 case and barely compatible in the 0.05 case. So another thing that we get here is that we get the AMOC is stabilized at a reduced strength. And the height of the overshoot that you see this most prominently in the 0.1. You don't really see it in the 0.05, seems to correlate with how much the AMOC was depressed. I've kind of thought of it almost like a spring, right? The more you depress it, the more it rebounds. There's a very quick return to pre-forcing levels. It basically just recovers. Next slide. And so these are our kind of other tests, the ones that I mentioned in terms of location and pre-forcing. So I've added on here some comparisons. So with the cyan and the blue lines, the cyan line is the 0.1 forcing that I mentioned before that has about 8 meters of sea level rise or so. The blue is our background. So for this one, what we did is we applied a 0.05 forcing in the Beaufort Gyre to mimic what Kaigwen's paper argued might have occurred, which is about an 800-year pre-forcing of the Beaufort Gyre. And we also added in a similar amount, 0.05, from the North Atlantic margins of ice sheets, arguing that they would have been contributing something as they deglaciate. And so what's interesting here is that even though the location of the forcing is now split between two different places, you can see that the effect on the AMOC is basically identical. Both cases seem to stabilize around a little bit more than 25 surges in overturning strength. So at the end of the blue trial, what we did is we applied a quick 100-year 50-year 0.2 Sverdrup forcing for two reasons. One, we wanted to see if 0.2 for 50 years caused a collapse the same way that 0.2 for 100 years did, and we found that it didn't. And we also wanted to test to what extent this affects the way that the AMOC recovers, and it doesn't seem to really affect it. It still shoots up and off the page. And the other thing is the green and red comparison is the comparison between forcing applied to the Beaufort Gyre of 0.2 and forcing applied to the Rudeman belt of the North Atlantic for at 0.2 for 100 years. One basically identically the same. The only interesting thing here is that the bottom of the North Atlantic run occurs a little bit sooner, which seems reasonable as applying forcing to the Beaufort Gyre. It requires a bit of time for it to exit the Arctic Ocean and make its way down to the North Atlantic. Whereas if you apply it directly to the North Atlantic, it's already there. But it seems so far in what we're looking at that location doesn't really matter if the effect is going to be the same. I'm getting assigned 2 minutes or?
Yeah, 2 minutes.
Okay, great. Can you go to the next slide? So this is just a quick bit on sea ice area. It's very similar because it's almost inversely correlated to the AMOC strength. As you dump fresh water, you get increase in Northern Hemisphere sea ice. And you again see kind of two types of modes. Either you totally collapse the AMOC and you get a peak sea ice of around 1.5 million kilometers squared, or you depress it and it just goes up a bit. It's very sensitive to forcing strength like the AMOC. Okay, I think I'm running out of time. I think I have one more result slide to back. Yeah, so I'll just mention this quickly. The way the recovery occurs is a polynya opens up in February in the Erminger Sea, which is very similar to that which was talked about in Pelletier et al. 2020, which talked about recovery from Dansgaard-Oshkosh oscillations. So it's interesting that we're getting a similar type of recovery. And I think that's it for me. You can, yeah, that's just what I said. You can go to the next slide. Yeah, so that's our conclusion. We produced a model with reasonable freshwater forcing, accurate trace gases, orbital parameters, and orography. The one difference is that we have a land CMAP set to LGM, but we're not sure if this is going to actually matter. And we have clear evidence of a bimodal AMOC where it's either on or off. And what we think was most interesting here is we got a natural millennial scale of shutdown without having to put that in by hand by forcing for 1,000 years. Okay, I think that's it. I'll just leave the next step slide up if there's any questions.
Okay, thank you. Any questions? Yes. We have Betty. Betty, go ahead.
So very interesting. Thank you for that talk. So have you looked at the newest iTrace simulation, which also includes pre-younger dryas forcing and more reasonable forcing during the younger dryas? It'd be interesting to compare what you found. And it uses CESM 1.2.
I haven't looked at it yet, no.
Okay, well, it's available on the climate data guide, earthsystemgrid.org.
Okay, I will definitely make a note to look at that.
Okay, more questions? I don't see any currently. Maybe a quick one. So how does the temperature compares to the proxy? So which so what's the best fit in terms of both fitting the temperature and the shutdown of the AMOC?
So we're still investigating the spatial distribution of the temperatures, but in general, they're correlated pretty strongly with the AMOC strength. They take a little bit longer to regress back to their values before an overshoot, but we're still undergoing that analysis. And the hope is to kind of overlay a map of what temperature changes we're seeing with proxies with the proxies that exist to try and tune that to see if we can get a compatible temperature change with the forcing levels that we've been using here. So I guess the answer is we don't know yet, but it's on our radar to look into that.
Okay, thank you. Okay, let's move on then. Next speaker is Yuting Xu. Extensive evidence for last interglacial analog of the 8.2K event.
Yeah, thank you. Let me just share my screen here. Okay, so yeah, my name is Yuxing, as in, have you seen the movie Yuxing? That's how you pronounce my name. I am a 6-year PhD student at Columbia University, and today I want to talk about the last interglacial analog of the glacial outburst event 8.2 thousand years ago. And this is a project I've been working on with my advisor, Jerry McManus. And just a quick note that this project is mostly about observation and it's not modeling. But if you stay patient and stay towards the end, I will touch on some implications of our project on the modeling of paleoclimates. But before we get into it, I just want to acknowledge that this project was helped by Julia Goshok, Sid Hemming, Cassandra Costa, and Wei Huang, without whom this project wouldn't be possible. So the 8.2K event was an abrupt climate change event in the Holocene. And here you can see a study on ice core data from Greenland that showed a large fluctuations in a variety of proxies around this time period. And similarly, there are marine studies that showed fluctuations in sea surface temperature, sea surface salinity, and bottom water flow speed that changed around the same period. So this is an event that had both air temperature and marine circulation impacts. So indeed, the 8.2K event, it was the largest abrupt climate change event during the entire Holocene period. A lesser known feature of this event is a red layer high in iron that was deposited in the Hudson Strait, as here pointed out by Barber et al. And on the right, I made a map of the North Atlantic. And the red dots here are a compilation of all previous studies that pointed out the presence of a red layer. You can see they span the Hudson Strait and also the coastal regions of the Labrador Sea. In 2012, Nicole and al. Found in 2 cores, sediment cores from the Labrador Sea, a layer of red sediments during the last interglacial, right? So not the current Holocene, but the last interglacial. And you can see here, this purple line is the red to green color reflectance data. You can see there is a sharp increase from the grayish bottom to red layer, and then slowly decreases. And the bottom contact of that red layer is pretty sharp. So that's a indication that this red layer was deposited pretty rapidly. And they dated these red layers to about middle, early last interglacial. This raises the possibility of an analog event of the 8.2K event during the last interglacial. And it also begs the question, can we find more cores with this red layer? So in this project, I surveyed all the drill core images in the central and western North Atlantic. And the answer is yes, we found 4 more cores with this red layer. And you can see that they all kind of stand out from their background grayish colored sediments. And from left to right is their distance away from the Hudson Strait, so increasing distance to the right. And if we plot all of the cores on a map, all of the red dots are the cores with a red layer, and the white dots are the ones that are without. And it seems to be that the distribution of the red layer follows the northwest Atlantic mid-ocean channel, here marked by this black line. And it also extends beyond it, right? So it is found in Bermuda Rise and also Carolina Slope. So this is a pretty astounding distance of spread, right? The straight line distance is about 3,000 kilometers from Carolina Slope to the Hudson Strait. And we're gonna focus on this core here to answer some fundamental questions about the red layer in terms of its age, its origin, and its delivery mechanism. So the first is its age. We measured benthic delta O18 on this core to place the red layer at about 125,000 years ago. And this is about 4,000 years after the onset of the last interglacial. And we'd like to note that the 8.2K event happened about 3.5 thousand years after the onset of Holocene. So that's some similarities shared between these 2 events. We also attempted to calculate the event duration. So there are a variety of proxies that we can look at to define this red layer. And there are 2 methods that we attempted to use to constrain the duration of this event. But without getting into details, all of these estimates we think are the upper limit, the overestimation of this event duration. But the shortest duration estimate we came to is from thorium excess profiling on this very narrow peak of the iron flux in our core. And that constrained this event to 126 years. And we know that the 8.2K event was estimated to be about 160 years. So that's another similarity between these 2 events. Okay, so in terms of origin, we looked at the calcium-strontium ratio, showing here in red of this core, as a proxy for the detrital carbonate. We also looked at the thorium normalized iron flux in this core as the presence of iron. Both proxies show a big jump in this red layer. And we also know that during the 8.2K event in the same core, it's the same story, increases in these 2 proxies. So we think that this means the Hudson Strait area is the only area where these two types of sediments, so red beds and detrital carbonates, intersect. So this increase of these two proxies is an indication that the origin of this red layer is very possibly the Hudson Strait region. Okay. So lastly, the delivery mechanism of this event, we see that this red layer is associated with very fine sediments, but deposited in a very high mass flux, so very rapidly deposited. This is in contrast to the Heinrich 11 layer in the same core, where you have high coarse fraction, likely caused by the presence of ice rafty debris, and again, high mass flux. And we also note that during the 8.2K event in this core, again, we have low coarse fraction and high mass flux. So what does that mean? We think that some kind of deep water density flow, so kind of like a underwater landslide, either a turbidity current or a debris flow. These are two categories of a density flow. They could rapidly deposit fine sediments in a very widespread region. Okay, so a quick summary here that we compared the 8.2K event and the last interglacial analog of the 8.2K event, and we see that there are similarities in terms of relative timing, in terms of their origin, and in terms of their delivery mechanism. And the difference is that the last interglacial analog seemed to occupy a wider spatial range and cover the NAMOC and also beyond, whereas the 8.2K event was restricted to the Hudson Strait and the coastal Labrador Sea in terms of the deposition of this red layer. So the last interglacial analog is a mouthful. So we came up with a name for this event. We call it the last interglacial Laurentide outburst, or LILO event. So the LILO event coincides with a range of global changes. This includes a slowdown of the North Atlantic deep water, here shown from Benfica Delta C13 data, a resumption of the Antarctic bottom water, shown here from orthogenic uranium, and a small increase in the Antarctic temperature, shown here from ice core data. So all of these are consistent with the bipolar seesaw theory when you have freshwater release into the North Atlantic. Our findings suggest that the mechanism that triggered the 8.2K event may be an integral part of the deglacial sequence of events, during which the final collapse of the Laurentide ice sheet takes place about 3.5 to 4,000 years after the full interglacial temperature is reached. So, okay, next we're going to switch to some potential implications for modeling the last interglacial climate. The first thing to note is that during the 8.2K event, the Laurentide ice sheet has a 10-meter sea level equivalent of ice volumes stored in it. And we're not sure whether this would be similar during the LILO event of the last interglacial. And we're not sure because the extent of the Laurentide ice sheet during the last interglacial is currently poorly constrained because of erosion of geological evidence by subsequent glacial advances. But if we are to assume that they share similar Laurentide configurations, then the implication would be that at 125,000 years ago, the Laurentide had 10-meter sea level equivalent of ice volume, right? That's a non-insignificant ice volume, and you can compare that to the Greenland, which had about 6.5 meters sea level equivalent of ice. So that's implication number one. This suggestion that the last interglacial Laurentide may not have deglaciated that fast is consistent with a recent presentation at AGU led by Daniel LeBlanc and Jeremy Chacun at Boston College and their colleagues that used cosmogenic nuclei on ice-roughy debris to suggest that the northern hemisphere ice sheets, including Laurentide, may be persisted in some sectors across many interglacial cycles. And if I remember her talk correctly, she mentioned that the implication is that on average, the Laurentide was probably only completely deglaciated for 1,000 years on average, every interglacial in the past interglacial cycles. So that's consistent with our study. Okay, so implication number 2, we have to remember that during the last interglacial at about 125,000 years ago, the global mean sea level was about 2 to 4.5 meters above the present level. But during the 8.2K event, the global mean sea level was about 14 meters below the present level. So there is a difference of about 16 to 18.5 meters difference of sea level between those two time periods, right? And somehow we have to reconcile the difference in the global mean sea level of up to 18.5 meters, while if we are to assume that the Laurentide was in similar configurations between these two periods. And I'm not sure exactly how that we can reconcile this, but one option, right, would be to have early melting of, you will need the Greenland ice sheet and the Antarctic ice sheet to have early melting during the last interglacial to reconcile this. But I'm of course also open to other suggestions. We're scratching our head about this. So in conclusion, the 8.2K and the LILO events share similarities in relative timing, origin, and delivery mechanism. The LILO event likely surpassed the 8.2K event in peak rate of meltwater discharge, and therefore leading to a more widespread distribution of the red layer. The Laurentide may have had 10 meters sea level equivalent of ice volume at 125,000 years ago, and that's during the early or mid last interglacial. And lastly, the two time periods have a difference in global mean sea level of about 18 meters, and that will require some kind of early melting of other ice sheets during the last interglacial. So this project is currently in review in geology, so stay tuned. And I'm happy to take any questions. If you want to get into touch, you can email me or connect with me on Twitter. Thank you very much.
Thank you very much for this very interesting talk. Are there any questions? Perhaps, yeah, there's one by Tripti.
Yeah, thanks for a great talk. I'm curious as to whether you can look at regions that are strongly sensitive to freshwater forcing in terms of hydroclimate to maybe find the signature of this event, or have you looked?
Yeah, I think I haven't looked at it, but I think that's a very good suggestion, and especially because we have constraints instead of trying to date this event. Benthic delta weighting is not the best way to date an event that's 120,000 years ago. But if there are, say, terrestrial records that can be absolutely dated, and they can find some kind of hydroclimate fluctuations around this period, then one, that will give us some more information about its age, but also yes, it'll give us more information about the kind of hydroclimate changes that happened during this period.
Okay, more questions? So I do have a question. It's quite interesting about the theory with the turbidity current and the wide transport of material into the basin. So my question is there any analog which would justify such a, I mean, it's quite happening in present day that you have these turbidity currents, but typically the material is transported kind of to the base of the rise and not vastly into the basin. So is there any analog from other times which would justify such a long transport on the basin?
Yeah, so there is, I think the currently modern observations that we have observed that the longest distance of kind of turbidity and density flow in general is about 1,000 kilometers in kind of traveling distance, and that was observed off the coast of Northwest Africa. But yeah, this is something new, right? This is 3,000 kilometers straight distance, and it's not very straight if you look at, right, the distribution is kind of a curve here. So it's even longer than that. And that's something that hasn't been observed in modern records, and it deserves some attention in terms of what kind of mechanism can push sediments this far from its origin.
Okay, Jesse, you have a question?
Yeah, great talk. I had a question about the timing here, because so what I find interesting is that you're finding the event occurring about the same amount of time after Heinrich event 11. Well, it's a little bit quicker, it looks like. But so with the 8.2, it occurs about 7,000 to 8,000 years after the last Heinrich event, which is about the spacing of time between Heinrich events themselves. So I'm wondering if you think there's any kind of connection there for determining what the spacing amount of time is after the previous Heinrich event before this kind of outflow event that you're finding.
That's a good question. I think, what do I think? I think, one, we need to better constrain Heinrich event 11, right? We kind of have a rough idea that it happened between maybe 130, 135,000 years ago, but we don't have absolute age constraint, I think, on Heinrich event 11 yet. But it is interesting that they happened some set amount of years after Heinrich events. But I think I would caution against kind of seeing the recurring nature of Heinrich events too much, reading too much into that, because I think the general thinking about Heinrich events now is that they're not really the spacing between the Heinrich events is more of a coincidence, I would say, than some kind of mechanism, and that's especially true if you go deeper in time and looking at Heinrich 3, Heinrich 4, Heinrich 5, and 6, those, and you can see more irregularities in terms of the spacing of Heinrich events. But I would say I'm open to it. It could be that, right, some kind of Heinrich events could this could be some kind of, I don't know, baby Heinrich events. Right, it's not really defined by the icebergs and the ice rafted debris, but maybe defined by instabilities that led to meltwater discharge.
Okay, thank you.
Okay, more question? I don't see any. Okay, then let's move forward. Thank you. And the next speaker is then Markus Loverstrom. Is the last interglacial warm period a good process analog for the future?
Yes. Hi, everybody. Can you see my screen?
Yes.
Okay, great. I think you can hear me as well, so good. All right, thank you very much for organizing and for having me. So today I'm going to talk about a project that I'm working on that is still in a fairly early stage. It's more of an exploratory study than anything else. And I'm working on this with my students at University of Arizona. So I have 3 students working on this project or related projects, and kind of all their collective work has led me to think about these ideas a little bit, and the results I'm going to show you today. All right, so I will just preface by saying that all the results I will show here today are going to be based on simulations with CESM2, and I obviously need to include more studies, more models in my analysis before I can come to some sort of conclusion that is robust across models and so on and so forth. All right. So the basic premise here is that we know that the Greenland ice sheet is deglaciating at an accelerated rate because of global warming. And we also know that the Greenland ice sheet has deglaciated in the past. Okay, so the last time that the Greenland ice sheet was severely or significantly deglaciated was in the last interglacial warm period. There was also some deglaciation in the mid-Holocene, but the last interglacial is really the big daddy of deglaciation events in the last, I don't know, 100,000 years or so. Okay, and these results here are showing the deglaciation of the Greenland ice sheet in the last interglacial period, simulated by, sorry, I have a pop-up window, sorry, just 1 second. All right, sorry about that. All right, so what is shown here is the deglaciation of the Greenland ice sheet in the last interglacial period, simulated by CESM2 in a transient simulation that was documented in Somers et al., published last year. And if you haven't seen this paper, I strongly recommend that you download it and take a look at it. It's a pretty good paper. Okay, so anyways, so what is happening is that the ice sheet is receding by quite a bit over the last interglacial warm period, and the total volume lost is something like 4 meters sea level equivalent as simulated by the model. And most of the mass is lost in the north and kind of in the southwest. You can see that there's a big wedge that is missing from the southwest. So I guess the question then is, could this happen under greenhouse gas forcing, first of all? And the answer to that question is probably yes. But then we can also ask ourselves, is the last interglacial a good analog for future Greenland ice sheet loss? And I'm going to show you some results where I'm kind of exploring these questions using CESM2 simulations as part of CMIP6. So even though they're included in the Greenland ice sheet, the ice sheet is prescribed. So it's responding it's interacting with the climate system itself, but is not changing its shape as the climate warms. Okay, so that's a limitation. So it would be really nice to do this type of analysis using the configuration of CESM2 with the interactive ice sheet component. All right, so we have a number of future scenarios. Okay, so some of them are, just release as much greenhouse gas forcing as we possibly can to the climate system, and some of them are, mitigated scenarios. And sorry, this chat thing keeps popping up. I will just leave it open, I think. Sorry about that. All right. So basically, we have different future scenarios, and currently we are kind of somewhere in the middle of this chart. So we are kind of following the SSP3 scenario right now, and that's obviously better than the SSP5 scenario where we develop fossil fuel capabilities and so on. But it's not as good as the mitigated scenarios that I kind of shown more on the left there. So for the sake of the analysis, I'm mostly going to focus on the SSP3 scenario and compare that to the last interglacial. Right. Okay, so how are the last interglacial and the future scenarios different? Well, so the last interglacial, and the period I'm focusing on here is the 127,000 year before present period, which is the simulation that is part of PMIP4. Okay, so it was a period with high northern hemisphere summer insolation. Okay, so what is shown in these figures up here is the insolation as a function of latitude and month of year. So you have month of year on the horizontal axis. And the top left panel is showing that the modern case, the pre-industrial case, and the top right panel is showing the difference between the last interglacial and the pre-industrial. So you can see that we have there's more insolation in the northern hemisphere summer, and there's less insolation in the northern hemisphere kind of fall and winter. Okay, the important thing here is that greenhouse gases are pretty much the same as pre-industrial. Okay, if you contrast that with the future scenarios, and again, I'm going to focus on the SSP3 case in this presentation. So we have, modern insolation is not going to change, over the timescales that we're interested in here. We're talking about things that will happen, in about a century or so. But the greenhouse gas concentration is increasing by crazy. Okay, so the figure in the bottom right is showing the change in atmospheric carbon dioxide through time. And at the end of the century, the greenhouse gas concentration, if you follow the SSP3 scenario, is going to be something like just shy of 1,000 ppm. Okay, so we have two different cases, one with high insolation and, pre-industrial greenhouse gases, another case with modern insolation, but high CO2. So the question is the response of the climate system the same to different forcing agents? And the way I'm going to address this is I'm going to focus on the surface mass balance of the Greenland ice sheet. So I'm going to use a bunch of abbreviations here. So SMB is surface mass balance, and then accumulation and ablation are abbreviated as ACC and ABL. Okay, and the way I'm going to analyze this is I'm basically just going to look at the surface mass balance from climatologies from different simulations. Okay, and then so I'm going to show a figure like this in the top left with the distribution of surface mass balance in millimeters per year, and then I'm going to show some bar charts showing how the different components are changing in the different different simulations. Right. So if you look at the pre-industrial control case, you can see that there is a lot of accumulation in the southeast. Okay, and that is primarily due to winter storms. Okay, so the figure on the right here is showing the distribution of precipitation between the winter months and the summer months. And where you have blue is dominated by winter, and where you have red is dominated by summer. And then the kind of 50% distribution line is shown by white. So you can kind of see that the winter storms are really only dominating the precipitation signal, I should say, in the southeast and kind of along the east coast, whereas the summer precipitation is dominating everywhere else. Okay. And if we, I will come back to that thing because it's going to be a little bit important here for the interpretation. But if we look at the SMB and the components of the SMB in the last interglacial simulation, you can see that there is more winter precipitation coming in the southeast, but there's kind of little change in terms of the precipitation, or I should say the accumulation over the interior of the ice sheet. But then you have much larger ablation zones along the margins, and the total surface mass balance for Greenland is down to less than 100 gigatons per year. Okay, if we look at the SSP3 case, we're kind of seeing a somewhat similar story in terms of ablation around the margins, but the precipitation in the southeast is reduced, and the precipitation or accumulation, I should say, in the interior is increased. So that's kind of curious. But if you look at the integrated quantities of these things, they are stacking up to pretty much exactly the same numbers, which is kind of remarkable. And I should say that this is probably model specific, and there's a whole bunch of caveats here. But in the SSP simulation in CESM3, I should say that these are 3 simulations that are kind of average as well. They are stacking up to exactly the same numbers as the last in the glacial, which is pretty remarkable. But the spatial signature of the different fields are slightly different. Okay, and just for completeness, I'm just showing the worst case scenario, and all bets are off if we're following this trajectory. Then we're going to get rid of the Greenland ice sheet in no time at all. Okay, so I'm glad that we're not following that trajectory anymore. All right, so the precipitation seasonality seems to be somewhat important. Okay, so we saw this one before, so this is the pre-industrial case. So just to repeat what I said before, so winter precipitation is dominating in the southeast, and then summer precipitation is dominating pretty much everywhere else. If we look at the last interglacial case, remember that we have a warmer northern hemisphere summer and a colder northern hemisphere winter. The distribution between winter and summer precipitation kind of looks the same as the pre-industrial, but it's just much more amplified. So we have more summer precipitation in the interior and more winter precipitation in the southeast. Okay, if we look at the future, so the greenhouse gas force simulations, then we are seeing an increase in summer precipitation in the interior, but there is actually a decrease in precipitation in the southeast. So that kind of suggests that winter storms are less frequent. Okay, so how do we make sense of all this then? Well, so what I'm going to show you now is the difference between precipitation between the greenhouse gas simulation and the last glacial. Okay, so in the summer months, so June, July, August, this is what the difference looks like. And you can see that over Greenland, there is a reduction in precipitation in the future scenario compared to the last glacial, but there's more precipitation in the summer months instead in the interior and kind of northern parts of the ice sheet. I should say that even though the summer precipitation seems to be key to this, to understanding the fate of the ice sheet, I haven't gone that far yet in terms of my analysis of that. So I would just say that it could be due to this increased precipitation in the north, could be due to increased storms in the summer, or it could be just Clausius-Clapeyron scaling. You go into a warmer world, you get more moisture in the air, etc., so you can get more rain out or precipitation. I don't know about that yet. I will keep doing a little bit more analysis on that. If we instead compare the winter months, this is what the model is suggesting. So we get this massive dry anomaly in the greenhouse gas forcing scenario in kind of over the central Atlantic and extending into the southeast of Greenland. Okay. So that's kind of curious. So how do we understand that then? Well, so the key to understanding this is shown here. Okay, so what I'm showing here is the difference in summer temperature between the last glacial and the pre-industrial on the left, and the greenhouse gas case with pre-industrial on the right. So you can see that in the last glacial case, there's a warming pretty much everywhere. Okay, whereas in the greenhouse gas case, greenhouse gas force case, there is a warming pretty much everywhere except for over the central North Atlantic. We actually see a cooling. Okay, and how do we understand this cooling? Well, first of all, this cooling is something that we actually see in observations as well, and in many other models. So what is shown on the left here is a number of figures basically showing the change in temperature projected for the future. So the top ones are based on observations over the last several decades, and the bottom left panel is showing the projection from IPCC into the future. Okay, and you can see that there's a warming pretty much everywhere except for in the central North Atlantic, which is precisely where CESM2 is also simulating a cooling. Okay, but remember that we didn't see the same cooling in the last glacial case. Okay, so how do we understand this cooling then? Well, it has to do with the overturning circulation. So in the last glacial case, what is shown here is the overturning stream function. Okay, so pre-industrial on the top, last glacial in the middle. Okay. And you can see that the pre-industrial and last glacial, they have a somewhat similar overturning strength. But if you look at the future scenario, the overturning is completely collapsed in the model. And this is something we see in many models from CMIP6. Okay, and the collapse of the overturning stream of the AMOC circulation is also leading to changes in the heat transport in the ocean and so on and so forth. And this is ultimately causing this cold anomaly in the North Atlantic. Okay, so there seems to be a difference, at least in terms of how the model is responding to high insulation versus greenhouse gas forcing. Okay, so how is this related then to precipitation? Well, what is happening is that we have, a number of different paths that storms usually take. So there is the main storm track across the North Atlantic is kind of flowing from North America to Europe, and it takes this path that sometimes comes in and kind of touches the southern edge of Greenland. So that's why we see a dominance of precipitation there in the winter months. There's also paths where storms are coming up the west coast of Greenland, and this is happening more in summer. This happens in winter as well, but it's much more dominant in summer. Okay, and then we have storms forming kind of southeast of Greenland, and they're doing their thing, and then they're moving up towards Scandinavia. So when we have in the future case where we have this cold anomaly, the cold surface air is basically creating a high pressure anomaly, which pushes the storm track further south. So we're getting a reduction in precipitation in the southeast. So that's how we can understand the reduction in precipitation in the southeast in the future simulation. And we don't see it in the Latin glacial case. Again, what is going on the west coast of Greenland, I haven't had time to look at in detail yet. So, but I will be able to report back to you maybe next time we have a meeting here. Okay. So, okay, so what's the implications for the evolution of the Greenland ice sheet then based on these results? So we saw that this is how the Latin glacial, how the Greenland ice sheet is responding in the Latin glacial simulation if you run it long enough. So what I've done here is I've just taken the footprint of the minimum ice extent at the Latin glacial, and I'm overlaying the so-called IMBY basins from modern observations. And then what I've done is the bar charts here is showing the surface mass balance and its components integrated over the entire Greenland ice sheet. But now I can also do the same in these different basins. Okay, so if you just look holistically at the entire Greenland ice sheet, then you can see that the last interglacial and the future scenario, they have pretty much the same values, which kind of suggests that, okay, maybe the deglaciation is the same in the two cases. But if you look at different components of the Greenland ice sheet, so if you focus on the southeast, I showed you that the precipitation is reduced in the greenhouse gas case, meaning that we get less mass accumulation in the southeast. We still have a positive surface mass balance, but it's like a half or a third maybe of the last glacial case. So
2 minutes.
Right. Okay. So this is not necessarily suggesting that we're going to get rid of the southeastern part of the Greenland ice sheet in the future, at least not in the short-term future, but it's not going to contribute to the overall mass balance of the Greenland ice sheet to the same extent as it does today. Okay, if you look in the southwest, the future case, the greenhouse gas force case, is actually has a more negative surface mass balance than the last glacial case. So it's possible that we're going to get rid of the southwestern part of the Greenland ice sheet at a faster rate than in the last glacial simulation. And if you look in the north, the last glacial case had a negative surface mass balance, but in the future case, we actually have a positive surface mass balance. So it's possible that we're not going to get rid of the northern parts of the ice sheet, at least not to the same extent. And these are very preliminary results, and you should take them with a huge grain of salt because it's based on a model. But if there's some validity to these results, it kind of suggests that the northern part of the ice sheet is not as sensitive to global warming as in the case of high insulation, meaning that it's not going to contribute to sea level rise to the same extent, which is potentially a good thing. All right. So in the interest of time, I think I'm just going to leave up my this slide, and I will happily take some questions. Thank you very much.
Thank you for this very interesting talk, which has implications for the future. So are there any questions from the audience? So what of interest is also how the Atlantic Ocean circulation evolves. And so have you assessed how much the precipitation, the increase in precipitation in the future scenarios versus that of the freshwater flux from the ice sheet contribute to the weakening of the AMOC?
Yeah, so that's unfortunately in these simulations, the Greenland ice sheet is prescribed at its observed extent. So it's not, we don't have, ice calving and things like that into the North Atlantic included in these simulations. So I would say that the weakening of collapse of the North Atlantic overturn circulation is probably not driven by the deglaciation of Greenland per se. I'm sure that if I analyze simulations where we have the interactive ice sheet, we will probably see slightly different results, where freshwater fluxes from the ice sheet is also helping to collapse the AMOC. And it's possible that a transient simulation in the Latin Glacier will also have a reduction of the AMOC. I haven't looked at that, but it's a good idea. And this, as I said before, this is an exploratory studies. I haven't really gone that far in my analysis yet, but yeah, it's definitely something that I should look at.
Okay, thank you. More questions? Well, any questions? I don't see any currently. Do you see any, Esther?
Not in the chat. I guess I have a question though, Marcus. Yeah, you mentioned, well, two things really. Starting with, might be interesting to look in the transient lig, although we don't have, I'm not sure we're conserving all the water of the Greenland melt that goes into the ocean, but it might be of interest to look at the response of AMOC in that run. But also one other difference between like the SSPs and the transient lig is the timescales involved. Whereas the transient lig meltdown occurred over like 5,000 years.
Right.
And
yeah,
we're really interested in like, the foreseeable future.
Right. So the results.
So.
Yeah, no, that's a very good point. And so the results I showed here in terms of comparing the Latin Glacier with the end of century simulation is based on the PMIP4 simulations. So the the glacial case also has a prescribed ice sheet. So it's an equilibrium simulation. Whereas the transient simulation is obviously, as you said, the deglaciation of the ice sheet is happening over thousands of years. But in terms of the spatial fingerprint, I guess, of the melting, there seems to be slightly different in the PMIP4 Latin glacial versus the CMIP6 future simulations.
It was interesting that the totals were similar though.
Exactly, yeah.
So there is some analogousness there anyway. Yeah. So, okay.
All right, well, thank you very much.
Yeah, thank you, Marcus, interesting.
So we return then at noon as mountain time with Lori Gorenstein stuff. So 50 minutes break.
Yeah. Okay, I'm going to share my screen with the slide. Um, where is it? Oh, here it is. And share. Okay.
Esther, you are unmuted. You're muted.
Oh, yeah, sorry. Yeah. Oh, thank you. I guess we should get started with our last session of our Paleo Working Climate Working Group. Paleoclimate Working Group, sorry. Our first speaker is Yuri Gorenstein.
Yes, hello.
Oh, hello. Would you like to share coming to us from the University of São Paulo in Brazil?
Thank you. Let me just share the screen. Sorry. Okay. Hi, everyone. I'm Yuri from University of São Paulo. I'm here to present the fully calibrated and updated mid-Holocene climate reconstruction for East and South America. This work has been a collaboration with other scientists, Luciana Prado and Lana Weiner from the São Paulo University, Paula Bianchini and Elder Yokoyama from the Brasilia University here in Brazil also, Michael Griffiths from the William Patterson Institute, William Patterson University in Wayne, USA, and Francesco Pausata from the Quebec University in Montreal, Canada. So I believe we are familiar with the mid-Holocene characteristics, but it was a time around 6,000 years before present when the summer pattern insolation was higher than present in the northern hemisphere of the planet, which created a warm peak, but it was in no way only a local effect. It was also seen in a lot of other parts of the globe. It was a global climate effect, this orbital forcing. And we're going to talk about, well, I'm going to talk about the effects that had on South America's climate. So just a quick review on South America's main precipitation forcings. We have the intertropical convergence zone, which is a year-long permanent feature that shifts to the hemisphere that's currently in the summer. So during December, January, February, the intertropical convergence zone brings precipitation to the south of the equator, and June, July, and August, it brings precipitation and moisture to the north. There's also the South Atlantic convergence zone, which happens in the rainy seasons for South America, also in summer on the southern hemisphere. It brings precipitation to the whole east coast of South America. And there's also other precipitation pressure anomalies and that develop some characteristics, such as the Bolivian high and the Chaco low, which create a flow of moisture in the continent region. And these features together form the South American monsoon system. This compilation I'm going to present is actually an update on the compilation made by Prado et al. In 2013. In 2013, there were 120 proxy studies that were compiled in this climate reconstruction for precipitation, surface temperature, lake levels, sea surface temperature, and sea surface salinity. Back then, there were 69 proxies that were from calibrated paleoarchives. Our compilation has added 57 new calibrated data and has presented not yet calibrated data that has not been yet calibrated from 51 of those paleoarchives that were presented in the 2013 compilation. So we're presenting 172 proxies from biological, physical, chemical, and isotopic fraction retrieved from calibrated paleoarchives only, and within the time interval of the mid-Holocene. The calibration was made by Paula Bianchini, Luciana Prado and Elder Yokoyama from the Geophysics Department, Geoscience Department of the Brazilian University. Many times, some paleoarchives may present hiatus and contamination from their excavation sites, which can present some mixture within the layers from the sediments, for example, and this mixture can get the ages mixed up within the same section, in the same section, so they get mixed up. And it's important to calibrate to analyze better and to reduce the uncertainties in the paleo reconstruction. In this work, the calibration was done using the Bacom software. This software, it uses a linear approach to approximate the age from all the proxies in the vertical sections from the paleoarchive. So in each vertical section, you have some of the data that has been calibrated due to their measurements of radiocarbon isotopes. And with these calibrated ages and the accumulation rate that the sediment has, you get a linear approximation for the full length of the vertical section and their supposed calibrated ages. It's important to reduce this kind of uncertainty when we're talking about paleoreconstructions, because they are used to validate and to calibrate numerical simulations that try to recreate past climates. And those numerical simulations carry on their own bias. They have uncertainties of their own and they carry some biases. And it's important not to propagate any kind of error. So with no further ado, let's show you the reconstructions. So first, the precipitation proxies. You see on the right side the South American map. The large box on the top left is the Amazon region defined by the IPCC assessment report number 5. The top right, smaller one, is the Northeast Brazil box, and the bottom one is the Southern South America box. The orange data means a drier mid-Holocene than present. The green means wetter, and the white ones mean similar to present. The circles are from sediments. The triangles exhibit the speleothems, and there are some small diamonds. Those diamonds are from soil samples. So first, we can see in the Amazon region box, there is one high, oh, sorry, I also forgot to say, the size from the data also shows the quality from this particular information and data. So the quality was defined by us. We define it as the number of information, the number of proxies that have been dated inside the Middle Holocene interval, divided by the length from that specific section of the paleoarchive. Okay, going back to the Amazon region box, we see here in the Carriacou Basin up north, on the North Hemisphere, wetter than present precipitation during wetter than present mid-Holocene than the present. It's in agreement with the rest of the south of the equator part of the box, the Amazonian box, which says a drier than present mid-Holocene. These regions are in anti-correlation due to the intertropical convergence zone shift north during the mid-Holocene, again because of the orbital forcings. There is one high-quality speleothem that points to a wetter than present Amazon box south of the equator. It has been discussed by Ward 2019 that this speleothem in particular shows a hiatus during the mid-Holocene time, and after some discussion and other proxy analysis in the same speleothem, it was actually stipulated and it was actually found that it's in agreement with the other local regions that point to a drier than present mid-Holocene. So to the bottom, the Southern South America box has almost all proxy data information pointing to a drier than present mid-Holocene. And there are some different information coming from its frontier with the Northeast region, which is the region with more confrontation, well, not confrontation, but local information that seems to diverge from the regional section. So we'll get right into it. For this region, it's especially useful to separate it in local smaller boxes. So we have here in the Northeast coast, the presence of some wetter than present paleo-information and data. For its frontier with the Amazon region box, the interior sites, we have a drier than present mid-Holocene, and its frontier with the Northeast, the Northeast frontier with the Southern South America presents a lot of erratic rainfall information. And that's actually in agreement with a lot of CMIP 5 and CMIP 6 models, which recreate the constraints of the orbital forcings of mid-Holocene, and they generate a weaker South America summer monsoon system, and implicates a significant bell shift from the South Atlantic convergence zone. So those inputs of wetter than present mid-Holocene actually agree with this kind of conclusion that this belt of intense precipitation has shifted a lot during this time. And this Northeast coast being wetter than present also agrees with with a weaker South Atlantic subtropical high and a modern dipole that is maintained but inverted during mid-Holocene, which is these interior sites in modern times present part of vegetated and florestated area with higher precipitation than the Northeast coast. So during mid-Holocene, this information says that the climate here was more homogeneous with a drier precipitation over the lands that nowadays we have forests, and high precipitation on the drier area. Moving on to the temperature proxies, we have the Southern South America with majority of proxies pointing to a warmer than present mid-Holocene. In its frontier with the Northeast Brazil, we have some other information that points again for some shifts and erratic position from the South Atlantic convergence zone, and pointing mostly with the higher quality to a colder than present mid-Holocene. So lake levels reconstruction, we can see the point, it agrees with the precipitation being lower during mid-Holocene. It overall points to lower lake levels all across the Amazon region box and the Northeast Southern South America frontier. The sea surface temperature proxies, they point to a kind of a separation between the 15 south latitude. Above this 15 south latitude, we have only warmer than present sea surface temperatures proxies, which confirms a high intensity and of the equatorial currents. Well, not high intensity, but this higher insolation pattern for the mid-Holocene presents higher and warmer surface waters on the coast of South America, and south of 15 degrees latitude, we have a cold and present sea surface salinity, sea surface temperatures. Surface salinity, we also have a agreement with the lake levels, the lower lake levels, and the drier South America continent proxies. We see all along the coast a majority of saltier than present sea surface salinity, all to the bottom of Argentina to the top of Northeast Brazil. There is only one lower quality proxy that points to a fresher sea surface salinity. But overall, it confirms the weaker rivers runoff to the ocean and collaborating with the saltier sea surface salinity. So in conclusion, we see that Amazonia presents a drier than present mid-Holocene, as in many studies has been discussed. The Northeast Brazil must be separated in individual regions because they have different patterns during this time and this epoch. Its coast was wetter than present, and its frontier with Northeast, the Northeast frontier with South and South America presents erratic precipitation. South and South America presents warmer and drier climates, and the coast can be separated from the 15 south latitude line to warm closer to the equator and colder under this 15 south latitude line, and the majority of the South American eastern coast has shown saltier conditions. I'd like to thank everyone, and I hope you enjoyed.
Thank you, Yuri. That was really great. Do we have questions for Yuri? Quite a lot. Oh, Tyler?
Hi, Yuri. Yeah, thanks for the talk. That's some really cool work. There are obviously a number of different models and interpretations of those models for explaining what was going on with mid-Holocene precipitation across Amazonia. And I'm wondering if you've compared your new proxy maps to any of the climate model output, kind of some of the different hypotheses regarding mid-Holocene precipitation.
Thank you, Tyler. Actually, it will be my next step on my research. We're going to compare it with the ESTHER modeling that has different forcings and inputs for the Green Sahara episodes. So we are expecting to compare it and to use it to validate the model, and even maybe some CMIP6 models. Those will be my next steps in my research. But thank you. I haven't yet done.
Are there any tropical storms who could have influenced your results in the past? I know they are very rare. You typically have a strong shear and horizontal winds, but occasionally they occur, and I was wondering whether you have looked into that.
Actually, I haven't looked specifically into that. Some paleoarchives may point to some kind of local response to a short-term episode, like a tropical storm or something like that, and it may reflect that, pointing to a wetter than present mid-Holocene. I haven't looked specifically for it. And that's why it's important to see a multi-proxy, to use a multi-proxy approach to get a global view from the whole regional place. But I haven't looked for specific local responses. I have tried to look at a more global, or not global, but the regional response of mid-Holocene forcing.
Okay, thank you.
I see a question in the chat, a couple of questions actually. I'll start with Alexander Thompson's. He says, thanks for the nice talk. why do you think the ITCZ shift north during the mid-Holocene, stays near the coast, and does not extend any further inland?
Oh, I see. There is this summer incursions of the ITCZ that often happen when the South Atlantic subtropical high gets weakened. So there might be some incursions in the coast due to this weaker South Atlantic subtropical high. So it possibilitates the precipitation in the coast, but the continent area, it's more influenced by this, because this part near the equator, it doesn't have a stabilized precipitation and rainy period. It rains year long. So when we're talking about this displacement of the ITCZ north, it mostly means that the Amazonia region is it's expected to be drier because it depends on year-long precipitation. And the coast of Northeast Brazil, it's not a year-long precipitation, it's mostly on summer. So it could mean that these two regions have differences in their precipitation expectation into this scenario.
We have another question in the chat from Bronwyn Konecki. She says, great talk. Can you comment more about the Paraiso record? True, there is a hiatus, but is that the entire reason it does not match the other records? Or do you think there is perhaps some seasonal sensitivity or other issue with interpreting the Delta 018 from that site?
Okay, yeah, that speleothem in specific was very discussed in Ward et al. 2019. I believe that Wang 2017 presented the speleothem and it reported a wetter than present Amazon. But in Ward's work, he explored, I believe, another proxy that was not the oxygen isotope. I can't remember right now. It was a karstic composition, but he said that the speleothem has a notable hiatus in the mid-Holocene. He clearly states that the information during this period is not clear at all, and using the delta oxygen isotope. So when he explored the nearby site speleothem with another type of proxy, he did found a drier than present Amazon region, but I can't say much further because I don't have the specifics in my mind right now. But if you look for it, you find it, and it's well written, and it's really enlightening to read the Ward work from 2019.
Maybe you could, if you know the reference, the citation, you could put it in the chat sure. When you're done. Bronwyn says she is familiar with the Ward paper, was just curious about your opinion. So anyway, thanks,
okay.
Bronwyn. Okay, anyone else have a comment or question? Anyway, all right. I think we can maybe get our next speaker with their talk ready to go. Our next speaker is Greta Shum from the University of Washington. If you just hold off, we'll make sure we start on time. And anytime you're ready now, Greta.
Okay, great. Thank you. I'm excited to be here today. My name is Greta Shum, and I'm working with Abigail Swan here at the University of Washington. I've listed my collaborators here. Marisa Legou is actually at the University of Saskatchewan at the Coldwater Lab and Center for Hydrology. Steve Warren and CC Bitts are here at the University of Washington. A few of us are also in the astrobiology department here, as well as the atmospheric sciences department. So this talk is about snowball Earth, but a lot of the implications are also relevant for looking at life on icy worlds outside of Earth. So as an introduction, there is geologic evidence that suggests at least 2 global glaciations or snowball episodes that took place about 700 million years ago. On the left, I'm showing you 2 early papers, one by Brian Harlan in 1964 and one by Douglas Mawson in 1949. They both independently came up with the idea of having a snowball Earth or global glaciation where ice extended to the equator. Mawson's theory was debunked, thinking in the wake of plate tectonics, and then brought back again. On the right, I'm showing you these sites that are basically worldwide of late Neoproterozoic glaciogenic deposits. And down below is this histogram of where the deposits are thought to have come from, based on where they would have been at the time. You can see that there's substantial evidence of deposits around the equator. So this suggests that ice did indeed reach all the way to the equator and there wasn't a water belt. Also, what's interesting is that these deposits are pretty uniformly distributed, but this histogram, these stair-stepping lines show the uniform distribution of what would have occurred if this had been uniform across a sphere. Yeah, so from a modeling perspective, this is also likely to have happened and is also generally a likely scenario on any Earth-like planet. So from a simple energy balance perspective, I'm showing you this generic plot that shows kind of the hysteresis that comes from a snowball Earth. So these yellow dots indicate stable states for our present climate. On the x-axis are showing the radiative forcing from concentrations of CO2 and also solar flux. So as you go to the left on either axis, you can see that the ice line latitude from our present state would move toward the equator up to a certain threshold at which it would move unstably toward the equator completely and snap into a snowball Earth. So, and this is a really stable regime. You can see that you only come out of it by building up carbon dioxide because your sinks are blocked, at which point you move very explosively again to D, which is the ice line latitude at 90, so at the pole. And then your weathering and other carbonate silicate cycles take place, and you can come back to point E, where radiative forcing is such that if you decrease again, you'll have this descending of the ice line latitude toward the tropics again. So this sort of diagram is based on these 1D energy balance models of the Boudico and Sellers type. And it just gives us a sense that snowball Earth is actually a pretty common type of scenario for an Earth-like planet. So if this is common, could life survive? What are the implications for life? And it's clear from fossil records actually that eukaryotic and photosynthetic life did survive this seemingly cataclysmic event. Not only did it survive, but it also seems to have undergone major diversification. There's some debate about whether the diversification occurred directly preceding the snowball events, which would have led to a decrease in CO2 and potentially the radiative forcing that would have led to the snowball event itself, or whether the diversification occurred after the snowball events when we came back into that hothouse climate. There's also been suggestions, even from the Mawson paper in 1949, that the snowball event was really critical for the Cambrian explosion and the rise of animals on Earth. So however it occurred, it's clear that Snowball Earth was an important chapter in the history of evolutionary biology. And so it's useful to understand how life as we know it survived throughout this period, and what kind of mechanism would have allowed for that to take place. So the question is, how could life survive such a catastrophic event like Snowball Earth? And the answer is pretty clear. We need surface level liquid water. And by surface level, I mean able to access sunlight for photosynthesis to occur. Now, whether that water is freshwater or ocean water is not really that important, because there are a lot of studies that show that the kind of life that survived, or that we have fossil records of, actually changed between freshwater and saltwater during this time as well. So any kind of liquid water will do from a life perspective. So I'm going to take you through three sort of sections of this talk. The first is to explain to you this hypothesis for how we think that life survived. The second is to describe the environmental conditions that would have enabled that to take place. And the third is the simulations that we've done and are continuing to do. So any input is welcome on the simulations. We're trying to use CESM to simulate a snowball Earth and the refugia, or oases of liquid water that would take place. So starting off with the refugia hypothesis, what environmental conditions could have allowed for open water to exist and surface life to survive? So in order to understand how surface liquid water could have been maintained, we need to understand something about ice dynamics on Snowball Earth. So what was the ocean like on Snowball Earth? Well, instead of being hard ice, you can actually think of the oceans as being moving, flowing, still, but made up of what has been called sea glaciers. So they're not restricted by the continental configuration at all, or they're not flowing on land, rather they're flowing in the ocean. Generally, the flow is equatorward from the poles, and you have net sublimation at the tropics. So these ice flows are moving and pushing into continents, including pushing into bays where the flow is restricted. So when you have glacier flow, you can morph to the topography that you're coming up against, but only to a certain extent, not water. So if you come up against a narrow bay, you may or may not be able to flow and invade all the way to the end. So what does this imply about how life survived on Snowball Earth? Well, there are three general hypotheses for how life could have survived. The first is volcanic hotspots. Of course, you can have local areas where volcanism allowed for ice melt and maintenance of liquid water. This is pretty temporary though, so it's not something that would be necessarily as sustainable as like a long-term refugia. The second hypothesis is transparent ice. So you could have what we often think about for Europa, for example, ice that's transparent and the sunlight can penetrate, and then liquid water can be maintained below the surface through geothermal heat. Again, this is subject to some variations in the environmental conditions that would have to stay in place for that to be maintained. The third hypothesis is that sea glaciers would flow, as I was describing, into narrow bays and get terminated early before they can invade all the way. This would allow for a water source, and also it would be surrounded by continent. So there would be transfer potentially between land, biology, and ocean. And this would also allow for interactions between the land surface, the atmosphere, and the ocean. So this is the hypothesis that I'm going to focus on in this talk, and we're going to discuss how likely these are and simulated. So just to get some of the details out about this hypothesis. It's described very well in Campbell et al. 2011. And the authors show that the geometry of a glacier invading a narrow bay is limited by the softness parameter and sublimation, net sublimation. It turns out that both of these are regulated primarily by land surface temperature. And the one that's most sensitive to land surface temperature is net sublimation. So if you have a higher temperature, you end up with less penetration and less invasion of the glacier, and then more likely refugia. So the takeaway is that you have a higher likelihood of a refugia or liquid water at the surface through this hypothesis if you have warm surface temperatures. Okay, so what we need are warm surface temperatures. The two levers that we can use in this scenario to sort of constrain a habitable zone using surface temperature warming are CO2 concentrations and darker surfaces. This is pretty straightforward. The mechanism that takes place here, as we saw, solar flux and CO2 are just the main drivers of temperature at large. The one thing to recognize, though, is that land surface albedo has an effect on land surface temperature very locally. And it's also possible to undergo a positive feedback. So if you have a warmer or a darker surface, you'll absorb more sunlight, melt snow, and even darker surface. So it has this feedback capability, whereas higher CO2 increases radiative forcing globally, uniformly across the planet. Okay, so these are our two levers, land surface albedo and CO2, the two controls that we'll use to alter the surface temperature. So now I'm going to describe to you these simulations that we've been doing. And like I said, they're ongoing. So I'm just going to show you some preliminary results, but stay tuned for more. So the goal of these simulations is to constrain the habitable zone of albedo and CO2 combinations for possible refugia. So in order to do that, there are two steps we have to take. First, we have to make a snowball and initiate it through different combinations that will be stable in a global climate model. And the second step is to test the climate space by changing albedo and CO2 concentrations. So this first step, non-trivial, make a snowball. Okay, so how do we do that? What we wanted to do is couple sea ice model, an ocean, a land model, and an atmosphere model together in order to make this snowball. So I'm going to take you through the choices that we've made, starting with the land model. So the goal specifically for the land model is to have a simple interface land model that's interactive. There are no plants on Snowball Earth. We want to be able to tune the land surface albedo directly without modifying anything else. This is kind of a difficult problem because CLM, the community land model, is really complicated. It's useful for representing Earth, but it's really hard to isolate albedo by itself without affecting a bunch of other things. Caveat is like, if we made all of the land surface soil, it would have been probably easier, but still, there are a lot of processes just embedded in CLM that make it hard to tune specifically land surface albedo. We would have had to change the type of soil. A lot of different aspects about this model are hard to distinguish if you're looking at what caused an atmospheric response like warming. Was it really the albedo change, or was it the evaporative resistance that was associated with that change in soil type? So while I love CLM, we chose a different model, which is the Simple Land Interface Model, or SLIM. It's an idealized land surface model that couples to the Community Earth System model in place of CLM. It's available on GitHub, and it's built by Marisa Legou, who is one of our collaborators. And you can see that it's much simpler than the schematic that I was just showing you. You can prescribe roughness, albedo, the bucket depth, and evaporative resistance. And it has this soil temperature gradient, so there's heat flow throughout this land surface. But it's a lot easier to work with if you're just trying to isolate processes associated with land-atmosphere interactions. You too can use SLIM if you think it would be a useful tool for you, and it's also being integrated right now into CESM as a land model. So you can either download it from the GitHub that I've put here or wait for it to come out as a comp set. Okay, so we use SLIM. We apply a uniform land surface albedo of 0.3 visible and 0.5 near IR. This is a pretty bright surface. If you think of like a sandy, bright desert. So we wanted to have a pretty strong reaction, at least for initiating the snowball. We apply uniform evaporative resistance of about 100 meters per second and uniform roughness of 0.1 meters. Okay, so that's our land surface model. What about our atmosphere model? The goal for the atmosphere model is to make radiative forcing conditions that would initiate a snowball. We use CAM5. We set orbital conditions pretty generically, but then have a solar constant that's about 91% of our modern. That's our radiative forcing that we're going to use to initiate this snowball. Okay, what about sea ice? So the goal for sea ice is to make sure that it doesn't break when we get to the tropics, because the sea ice is really not meant to advance all the way to the tropics. So we wanted to simplify this as much as possible and make sure that everything runs smoothly. We use the sea ice 5 Los Alamos sea ice model. We turn dynamics off. And we run it in thermo only, because the thing that we want is for it to melt when it's warm and to form when it's cold. This was not necessarily that straightforward. We have to initiate a salinity profile manually and then increase the coupling frequency and reduce the number of thickness categories to 1. For our ocean, our slab ocean, we wanted to use slab ocean with fixed Q fluxes, but no matter what we did, we could not get the water belt to go away. This was after 50 years of simulation. So in the end, what we did was we removed lateral heat flow in the ocean, so set our Q fluxes to 0, and voila, a beautiful snowball forms. What you'll notice is it forms pretty quickly in about 17 years. And if you look closely, there's like a little blip in the Mediterranean that there's some melting that occurs throughout at some points in the year. So this isn't, we weren't sure how long this would last as a snowball. Is it just going to be a temper and then come right back out? So actually ran this simulation for about 100 years. And after 100 years, it stays pretty frozen, but there still is melting in the Red Sea and the Mediterranean, which are places that look a lot like nearly enclosed bays, like what Refugia would want. This is a comparison of our P-C to P-C from Pollard and casting. Okay, thank you. And you can see just generally the patterns are pretty consistent. So we have a scale here that's linear, whereas this one is not super linear, but you can see that there's net sublimation in the subtropics, and then a little bit of net precipitation in the equator. But overall, the kind of pattern of sublimation, like precipitation, net sublimation, net precipitation at the high latitudes is pretty good. So we consider this a pretty good snowball. Okay, so the last step is to test the climate space by changing albedo and CO2 concentrations. I'm going to show you just our preliminary results and end with this, but I'm going to show you this first simulation at 0.3 albedo and 10 parts per million, and we increased CO2 and we also increased albedo. I'm going to show you what the results of land surface temperature are, which is what we care about. So generally, the land surface sees a temperature of about freezing and colder. At different parts of the year, it does get above freezing in this 10 parts per million case. But in the annual mean, it stays around 0 at most. And as you can see, just kind of like taking a overall glance at this, increasing CO2 generally has a weaker effect than increasing land surface albedo. And if you get to 0.1, this is about the color of dark sandy beach, which can get pretty hot, as you might know from walking on a beach. So this is a pretty strong effect, and these are generally values of soil albedo that are commonly seen on the present Earth, so they're not unrealistic. So just by increasing the darkness of our soil, we can get a really strong response in the likelihood of hosting life. Our next steps are to do this in an idealized way. So we did this with modern continents, which has been done for other snowball Earth simulations and is useful for comparing to modern atmospheres, but we're hoping to do it just for an idealized continent, changing the geometry of our early red seas, and also kind of comparing that effect to what I've shown before, the change in albedo and the change in CO2. Also maybe doing realistic continental configurations, but I guess I would love input from others on how feasible that would be, because I've looked briefly into changing the continental configuration, and yeah, I'm not super confident on that yet. So I've shown you sort of this exploration of how life could have existed on Snowball Earth and on other icy worlds. I just want to thank my collaborators and also David Bailey at NCAR, who has been super helpful in getting these simulations going. And welcome more help from all of you as well who have more experience with paleo simulations. With that, I'll open it for questions.
Thank you, Greta. That was really interesting, really cool results. And let's see if we have some questions.
So, Greta, what is the causes of the change into the icehouse world? I mean, so you're changing the albedo and CO2, but so what's the trigger and how do you come out?
Of Snowball Earth? Yeah, to get into a snowball, we are applying this lower total solar irradiance, which was slightly non-trivial. You have to like produce a new solar file. But in the real world, I guess the entrance into Snowball Earth, I think, was a combination. There's like a 2021 paper by Mitchell et al. That talks about the orbital configurations that would have led to glaciation. So that's a solar flux change. But like I said, there are also these suggestions that a huge spurt in life caused a drawdown of CO2 and then slip into Snowball Earth. Then how do you come out? It's pretty well established that you come out by building up a lot of CO2 and then melting really fast. And even the deposits that have found that, you know, are evidence for Snowball Earth, almost all of them are overlaid with these like cap carbonates that are very distinct and show just a quick return to a really hot house climate. So you get out by building up a lot of CO2 because you can't absorb it into the oceans.
And so how are weathering changes? Could they not play a role in these, and they may even alter your land surface?
Yes, this is something that I would like to think more about. There have been some papers about the role of dust in, you know, changing the land surface albedo. So if you have ice as an ocean, it's going to have an effect on wind. So wind is going to be completely different in this and totally based on topography. And so you can actually build up a lot of dust. And when you, I guess like your question is probably about carbonate sinks, but I've been thinking about weathering from a perspective of albedo. But yeah, I guess the realism of our simulations with respect to like how we enter and leave Snowball Earth is pretty minimal. But as long as we're in Snowball Earth, I guess our focus has been on how do you maintain liquid water even while having a shut ocean without opening up an ocean. Yeah.
Okay, thank you.
Mm-hmm.
There's a question in the chat. We have about a minute from Paul Acosta. He asks, well, he says, very interesting talk. Both POP and CAM use a specified topobathymetry, but can SLIM allow a modified paleogeography?
Right. This is the question, and I think that's the problem that I'm coming up against in modifying the paleogeography is integrating it with SLIM, because there are just like some, I guess they're domain files that CLM has to use to interact with CAM, and I think I just have to manually modify them in SLIM to match what would need to happen in CLM. So I think with CAM 6, this is easier, I think, with CLM. But as you probably guessed, SLIM was built to be compatible with CAM 5. And so updating SLIM is just going to be tricky. But if Paul, you're interested in having a chat with me over Zoom, I would love to talk to you about how to make that work.
Okay, thank you, Greta. That was excellent. And I think we should move on to our last speaker before discussion, Tyler Kukla from Colorado State University.
Thanks. Just a moment to, I'll share my screen now.
Sure.
Okay. Is it showing here?
No.
Oh.
It says, there we go.
Okay, cool. Great. Well, yeah, thank you so much. My name is Tyler Kukla. I'm a postdoc at Colorado State, and I have to tell you right up front that I have no modeling results to share with you today. I'm really excited to talk about a resource that my colleagues and I have been developing over the past few years called the Patch Lab. This is an online database and workspace where you can find and download Cenozoic stable isotope data, largely from terrestrial deposits. And the reason I'm excited to share this with you is that we think that this could be a useful tool for a number of different proxy model comparison studies. The first thing I want to do, however, is just take a moment to acknowledge my phenomenal colleagues and collaborators on this project. Jeremy and Ellie from Colorado State, Dan from Brown, and Paige from Stanford have all contributed significantly to the development of this database and deserve a tremendous amount of credit. It's been really awesome to work with these people. The Patch Lab itself is born out of a couple of different motivations. One of them is simply that it takes a lot of work, as I can attest to compile all of these stable isotope data into one place. And another is that, well, of course, we want to make it easy to download it because it is so labor intensive, but we also want to make it easier to access additional dimensions of these paleoclimate data archives. And when I say additional dimensions, I mean more use of the spatial dimension in different analyses, as well as the dimension of multi-proxy comparisons, comparing one proxy signal to another to look at when they match up and when they deviate, and trying to understand how those make sense through time. These are two things that I think can benefit a lot as well from comparison to models. This is a resource that's in active development. You can see that our data coverage right now is North America, Europe, and Asia, and we have a lot to fill in, and we're adding new data every week. It's available for use right now, and I'll take you to the site at the very end of this talk. But we do think that it's ready for application to certain paleoclimate or proxy model comparison problems. And so this is why it is available, but we are adding new data to increase the coverage. There's one thing that I worked pretty hard to get right in this that is coming back to bite me right now, is that honestly, it's a pretty simple resource, I think. I think that it's pretty user-friendly, and we don't need me to spend 20 minutes walking through how to use this. I didn't anticipate the privilege of having 20 minutes to talk with you all today. So I want to use just a little bit of this time. I know in the last talk before the break, and we'll probably wrap up a little early, I want to use a little bit of this time to talk about one feature of the Patch Lab, which is that it has multiple different proxies, proxy materials and proxy systems archived in it, and how this can be used to address one of the emerging themes of this meeting so far, which is the importance of having seasonal data that we can have in our proxies to compare to climate model output. This was discussed a lot on the first day in the North American monsoon talks. If we want to look at the strength of different seasonal air masses and climatic trends in the past, it's really useful to have proxies that can inform seasonal patterns. And the Patch Lab is one opportunity to develop and address some of these challenges, because Multi-proxy comparisons are one of the ways that we can inform seasonal trends in the past. These are just a few papers that have done this. Polisar et al. In 2021, for example, looks at bivalve delta O18 along with soil carbonate delta O18 to kind of back out the seasonal components and their contributions to longer term trends that soil carbonates can take up. I want to talk about briefly just one other way to do this, which is by comparing two different proxy materials that have different sensitivities to seasonality. This goes into the importance of selecting which proxies are going to use for a proxy model comparison and how to interpret them, and emphasizes some of the important things we should be thinking about when we're developing new proxy system models that can translate climate model output to our proxy results. So the one example that I want to talk about here is one that dates back to the late 90s and early 2000s, which I'm going to call big delta. It's just the isotopic composition of off-edemic clay minerals minus the isotopic composition of soil carbonates. So we're looking really only in soils here. And big delta is useful because, or one of the reasons it's useful is that clays and carbonates are giving us the same proxy information. We have a good expectation of what our big delta value should be. It should be right around 0 once we subtract out this co-equilibrium value, which is a basically constant offset between these minerals at a wide range of environmental temperatures. So what this means is that if our big delta is 0 on this x-axis I'm showing you on the bottom, then we don't gain any new information from looking at one proxy over the other. But if our big delta deviates from 0, there's the potential that there's more information that can be understood in this system, and that the coupled proxy system can help constrain additional dimensions of climate or of proxy formation or one thing or another. And the key point here is that not a ton of studies have looked at big delta in the past, but the ones that have found that big delta is rarely at 0. We have a good spread of deviation, and Tabor and Montañez and Stern et al. In particular argue that a lot of these deviations from 0 can be related to the seasonality of precipitation. So this is something that we wanted to test with the Patch Lab data looking at the Western US. The way that this framework works, before I dive into the Western US case, is basically that soil carbonates, we know pretty well, like to form under warmer and drier climatic conditions. They can also take on seasonal biases and form on short timescales. Clays form much more slowly and they have a wetter bias relative to soil carbonates. So if we have some information about the seasonality of O18, we can imagine if we have a low delta O18 wet season, that the clay values will take on that relatively lower O18 value and relative to the carbonates, and our big delta will be more negative. A stronger seasonal bias between these two minerals will lead to a more negative big delta if the low O18 season is the wet season. And the inverse is true when the high O18 season is the wet season. In this case, the clay O18 takes on the higher value, big delta is more positive, and in a more seasonal bias between these two different minerals, we might expect a higher big delta. This is the basic interpretive framework that we can use to compare these minerals to get at this additional dimension of climate. Western US is a good place to kind of test this. So we did this using Patch Lab data. We don't have actual modern soil data, and this is a next step. But using Patch Lab data, we are going to cover this range here, split into 3 domains, the West, Central, and East. And what I want you to notice is that these domains cover different regions of precipitation seasonality. The bluer colors on this map indicate a more winter wet climate, and the lighter colors, the whiter colors, indicate a more spring and summer wet climate. So this is the monthly precipitation in the Western domain here, with mostly winter wet precipitation. The Central domain is something in between, and the Eastern domain is more spring and summer wet. This is the seasonal pattern of O18 in all of these domains. What I want to point out is that if you just have tooth enamel or bivalve data that allows you to get at this kind of near monthly resolution, you probably won't have enough information to distinguish a winter wet from a summer wet climate using this seasonal information alone. What I mean by that is that the Western and Eastern O18 seasonality trends are really similar to one another, even though the actual timing of precipitation throughout the year is very different. So this approach alone is not always going to be very useful for teasing out relative changes in how winter wet versus summer wet your climate could be. So again, delta is kind of one way around this because the formation of these minerals themselves is one of the things that responds to the seasonality of precipitation. Here, I'm just imprinting what the Western US interpretive framework would be for big delta. We know that low delta 18 is the winter and high delta 18 is the summer. Tripty really nicely discussed how this is related to, largely related to changes in the type of precipitation that's happening, whether it's stratiform or convective, and how much evaporation is being incorporated in those different precipitation types. And for that reason, and also based on isotope-enabled models that have been run in much warmer climates with very different topography, this basic trend of low delta 18 winters and high delta 18 summers has likely held throughout at least the Cenozoic and probably longer. So what we've done is we compiled all these data from the patch lab looking at clays and carbonates spanning these 3 domains, west, central, and east, up on the top left. And as a reminder, the interpretive framework is more winter wet is more negative and more summer wet is more positive. I'm going to show 2 different time slices of data, pre and post OHT. OHT here is the open habitat transition. This occurred around 25 million years ago. And it's a time where there was major forest dieback across the Western US and the expansion of these grassy or open habitats that dominate a lot of the Western US lowlands today. Again, because we have this strong seasonal gradient today, we kind of know what to expect if the proxy system is working the way that we think that it is, which is that we expect more negative big delta values in the West, where it's more winter wet, and more positive values in the East. So I'll show you the post-OHT data first, because these are the closest to modern. These are, if we're going to capture this trend, we most likely expect it to occur in the most recent samples. And I'm going to show west, central, and east in these colors here. And remember that pre-OHT is just a more forested landscape and post is a grassier landscape. So in the last 20 million years or so, the data show a more negative delta value in the more winter wet western domain, getting to more positive values as you get to the east. And it demonstrates that we think that at least our proxy system is telling us what we expect it to be telling us, that there is some information about precipitation seasonality encoded in the difference between these proxy materials. Back when forests were more dominant across the landscape, in all of these domains, our data suggests a more winter wet climate, suggesting that when conditions were wetter, it was largely due to more wintertime moisture that supported these forests. So the Western US could become less winter wet as grasslands expanded. What I want you to take from this, though, is largely that these are 2 differently distinct trends in delta 18, depending on which proxy material we're looking at. So this is the last 50 million years, and I have the data scaled to the same axis from all of these different domains, the west, central, and east for the soil carbonates. And then here are the clays. And there's a statistically significant positive shift in the clay 018 data in each of these domains here. And the point here is that these diverging trends that we interpret to reflect changes in the seasonality of precipitation, from just the clay data or just the carbonate data alone, it's not really obvious that there is a seasonal signal here. I think many of us that are familiar with isotopes in the water cycle could sit down over a few hours and come up with maybe a dozen different ways to explain just the carbonate record or just the clay record, but there are fewer ways to explain them both together, and seasonality is one of these ways. So I'm going to cut off in just a moment, and we're going to look at the patch lab itself. But before we do, what I want you to really take from this is that the patch lab provides different types of proxy materials, and different proxies can, and I think in many cases should, respond differently to certain forcings. This is one example of this potentially happening in the Cenozoic, along with the expansion of grasslands. And these differences can encode useful information for proxy model comparisons, in this case, the seasonality of precipitation, allowing the use of multiple different types of proxies to strengthen how we compare our proxy data to models and getting at additional dimensions of the climate system that are otherwise challenging to inform, such as precipitation seasonality. This is one, I think, cool feature of the database. And again, it's pretty simple. So I'll take just a minute or 2 to kind of show you how it looks and how to access it now. And I'll have to stop sharing so I can switch over to that screen. So bear with me for just a moment here. Okay. Okay, so has this popped up on everybody's screen here? Cool. So this is the homepage. You start off right at the place where you can download a bunch of different data. You can filter by sample type or age and location. You can also filter by the first author's last name or the publication year. And here is the map of all the data that are in there currently along the stem of the proxy types through time. And then you can download the data here at the bottom. After you filtered, this map will update as you apply different filters. And in our data use policy, we indicate that as much as it is possible to cite every paper that you have downloaded and included in any work, to make sure that the original authors get credit. We have two additional resources on here, a graphical user interface model for vapor transport of oxygen isotopes. This is a one-dimensional storm track model. I've tested it against BCM and ESM output in the past and found pretty good results. So it seems that this is maybe a useful way to simplify some of the processes, or at least develop some initial interpretation of proxy data. I'm not sure how useful this will be for this group here. There's a soil respiration model, graphical user interface for looking at how carbon isotopes in soils can relate to atmospheric CO2 or soil respiration and productivity. A place to upload data with a flow chart for how that process works, along with the data curators, and a diagnostic test to make sure that your data are as compatible as possible with the data that exist. You can upload data that are not compatible, and the curators will help you make it compatible throughout the process. One thing I want to draw your attention to are the community tools. These are things that I hope to bring the proxy and modeling groups more together by just providing a place to identify things that others might not have used before or heard of. I have just some really basic ones on here, including different databases on the top and different types of hydroclimate models here on the bottom. I also have code at the top here, and only one that's linked right now is just companion code for this. One of the features here is that there's a script to translate the isotopic values into water isotope data with just a little bit of effort. But if you have any code that you'd like to share that's relevant for stable isotope paleoclimate reconstruction and proxy model comparison, I would be really thrilled to display that here as well. Or if you have any other tools or models or databases that you think would fit well with this resource, I would be really happy to include that here. So this is kind of my call to action at the moment. So that's it. This is a really pretty simple database. It's, again, under active development, and we're adding new data all the time. Any data that you have that maybe isn't here, please do feel free to submit it or just alert me to it and I can add it myself. And yeah, I think that this could be a useful tool for proxy model comparison work. And I'm excited to hear your thoughts or get any feedback that you might have. Also, this is very new. We just launched it a couple of weeks ago. So if you find any bugs, please let me know and I can squash them as quickly as possible. Thank you all for your time.
Thank you, Tyler. That was really cool. Really interesting results and tool. Maybe you could put into the chat the link to your patch.
That's a great idea. Thank you.
Yeah. Oh, Alana Weiner has a comment here. She says, very cool database tool. Sorry to see that the Southern Hemisphere is empty.
Alana, I am sorry to see that too. This is a development over a number of different years where we ourselves are working on Northern Hemisphere projects. And so we kind of, put that together based on the data that we were already compiling and that we're switching over to the Southern Hemisphere right now. So stay tuned and hopefully we will have more in the coming months.
And Tripti has a comment. Thanks, Tyler. I wonder if there's a way to add a simple interface for plotting model output from the ESGF for exploratory analyses.
Yeah, Tripti, you are reading our minds. This is something we would really like to add. Our goal is to look for a little bit of funding to maybe have a student or a postdoc to develop an interface like this. And something we would also like to do is build in an ability to upload like temperature files and then directly compute the meteoric water or fluid water values based on temperature fractionations. So increasing the ways that we can can combine the proxy data with model output is one of our next steps that we hope to tackle soon. I don't have the time for it at the moment to build in something quite as complicated as what I've just described, but we're looking for funding to put that together and building some proposals.
Cool. Jean Zhu has a question.
Thank you, Tyler. This is exciting. I will definitely check it out. I have a question regarding the database collection. So right now, do you have information, or can you filter the data by the elevation they're supposed to reflect?
That's a good question. Right now, there's no functionality for filtering by elevation. Part of the reason for this is that the data span back about 100 million years, and paleo elevations are really under constrained in many cases. The elevation itself, once you get back that far, becomes an interpretation rather than actual like metadata or anything to go along with the data. And we didn't want to impose interpretations like that on the existing data. In some cases, the authors did provide interpretations about this, and we include that in like accessory or additional columns in the database.
Okay, thank you.
Yeah.
Any other questions for Tyler?
So are you using paleo maps for the past data if you plot them, or you using the present day geography? And what's your plan with that?
Yeah, this is a really great question. Thank you. All of the lat longs are based on where the samples were collected from in the database. So that's present day geography. I spent, gosh, like a couple of months trying to get in paleo latitudes and longitudes built in using a variety of different resources. And I ran into a couple of challenges where like some plates, it would track the movement of a plate through time, and some plates would disappear or reappear, and then I would get NA values. And I don't know if other people have done this in maybe a better way. I would love, some insights on easier ways to do this. But right now we don't have paleo latitude or longitude in there. And it's not for a lack of trying, it's for a lack of my ability to succeed in this regard. Yeah, thanks for your question.
Any other questions?
Thanks, Tripti, for the comment.
Yeah. Oh, Tripti has a comment. Emily Judd in the pause seminar later, which is coming up at 2 p.m. everyone, might be able to help. She just put together a Phanerozoic temperature database for their project. So,
awesome. Yeah, that's super helpful. Thank you.
Yeah. Okay. Well, thanks for that demonstration and model results. That was kind of cool. And last chance for questions, Tyler. I don't.
Well, thank you all for the opportunity. It was a pleasure to share this
thank
with
you,
you
Tyler.
today.
I guess we can move on into our discussion period right before the break, before the Paleo Advances webinar series. And I will put up a slide for our discussion. This is it. Okay. So I'll open it up to any comments or questions, but I have basically the same questions that I had up in our earlier discussions over the last couple of days. If anyone has any further thoughts, or any of the people who have joined today for the first time, I'm asking the community what modeling capabilities would help in their research. And for past to future applications, what simulations or time periods should be a new or renewed focus. The upcoming proposal for computer time through the Climate System Lab. And then just ways to increase engagement in the Paleo Working Group activities. And just between modelers and and the data community as well, which I think Tyler just gave us a good mechanism for doing such a thing. So. Anyone have any comments or anything that I spoke about earlier today, any of our simulations? Arnie, have any thoughts?
Well, I do have a couple of thoughts, and that's related to greater talks. I know that Anka has done some idealized simulations. Often you do that testing that when you're testing new model version, either an ocean only simulation with no continents. Occasionally one have done also, I know multiple institutions have done that with idealized continent configuration, and so that is of interest to actually see what's the response of the geography to the climate. So for example, I remember that John Kurzbach and I worked a long time ago with the octagon continent. We never published some of these results, but I think that these idealized continental configuration may be of interest. I know that multiple institutions have worked on it, and I don't know whether that's just a single interest or community interest, but particularly if you go deeper in time, it may be of great interest. But it's also better to understand the present, past, or more recent past. Yeah.
Mm-hmm. Yeah, it's something to think about. Yeah, we have done, well, some Clay and Michael Irby did some idealized simulations, but not with the continental configuration, just with different greenhouse gas levels and orbital parameters. But
yeah, just to follow up on that, I'm very interested in idealized continental configurations, just to inspect, mechanisms at play and to get just simplified views of things, and to have it, like levels of complexity in the models, I think is really useful. One thing that we haven't set up these idealized continental simulations yet, but we're hoping to, instead of having an ocean, have the ocean be land, and just have it be ice-covered land with a very high albedo, and then have the ocean at different points as the nearly enclosed bays. So this will be, I think, and also maybe do it with the slab ocean and see what the differences are. But I think some of the snowball Earth experiments that have been done in the past that I was trying to compare with, our snowball simulation are like all aqua planet and idealized. So it's useful even just like within, the history of what's been done to just keep it idealized. But it's also partly because I'm scared of making bad paleogeography, probably too.
Betty put in the chat that Clay also did some idealized continental configurations that I wasn't aware of. Yeah, there is an aquaplanet version of available through the CESM as well. Jean, okay, Jean has put the link in the chat, so that's good to know. Clay's paper. Yeah, it's good to see that SLIM was used in your modeling work. It's good. I know it's hard to manipulate or make a new ocean grid for a dynamical ocean with, say, like a one large continent kind of in the tropics, like a Pangea type of a continent. That's kind of hard to do with the grids that we're familiar with. So just the way that you need to put a grid pole inland. So it's kind of hard when the land is just one giant continent to have different grid poles in there, because then on the other side of the earth where there's no land and it's all ocean, your grid is kind of stretched into larger grid boxes. So, and
yeah, we may have to just make the ocean like a tiny dot at the pole, and then make the lakes, or make the refugia into lakes that would freeze when it gets cold. But my preference would be to like actually use the sea ice model. So yeah, but I think what you're saying is that might be a little unfeasible.
yeah, I mean, maybe you could have really small polar land masses.
Yeah.
Or, yeah, yeah. So, Jean, you look like you have you're unmuted. So do you have something to add? Jean has a lot of experience with different continental configurations and things. So
I'm just curious whether it's feasible to put the pools at lower latitudes.
yeah, I don't know. I mean, there was a point a long time ago where someone wanted to do that, and it was the code that we had that made the grid didn't work very well in that situation. It blew up. I can't remember the problems, but it was difficult. Maybe Christine can remember.
Yeah, so
you recall that, Christine?
Yeah, we actually did an Ordovician run where we rotated the grid. So we put the poles on equatorial islands. So we did this rotation of the grid, so like by 90 degrees, and then put the equator, put the pole, the poles out on the equatorial islands, and then rotated it back. And then we actually did manage to get that to work, and we ran, but it is a little complicated to do because you have to, there's added steps with the grid rotation. It's not impossible, but there's added steps. And then you have to modify POP in a few ways. I'm happy to like give you my document on how I did that, but this was with like CESM3. So I think for POP, the procedure would probably be similar, but I don't know what other complications you may get with the other components of the model, particularly like the new sea ice. So yeah, but shoot me an email and I'll send you all the stuff I did.
That would be great, even just to hear an overview of what it took, because yeah, that has been my experience. Like once you change one thing, it just causes a cascade of issues with the other ones. So yeah, if it's, I mean, I can totally see why it would be just simpler to just make a tiny ocean at the pole or something and make it lakes. And yeah, it seems like a much easier route to the same outcome. But it would also just be interesting to hear what it took to do that. So yeah, I'll reach out.
Yeah, I'm sure. I mean, if you don't really, we did that rotation because we cared about the whole ocean circulation. If you don't care about that, then it's really not worth the effort. Yeah. But yeah, send me an email, shields@ucar.
Sorry, Betty, you.
So I'm not as fast as Jean at putting things in the chat, but so I'll do this after I speak. But you and others might be interested in a cross-working group meeting at the last CESM workshop called Alternative Earths. And so we had people speaking on early Earth and, different chemistry in that, but also exoplanets. So there were some great talks. So yeah, I'll put that in the link for everyone who might be interested. There's a YouTube video you can watch.
Yeah, that sounds super interesting. Thank you for the link. Yeah.
Okay. Don't see anything in the chat. So does anyone have any thoughts on interesting simulations that could be a new or renewed focus for the next CSL proposal? These would be, big community level simulations that would be of benefit to the community once complete, and they'd be like released to the community. Betty put a link into the Alternative Earths cross-working group YouTube from the last workshop. Don't see any thoughts on new simulations. Any other, Betty? You have
Since no one wants to speak.
Yeah.
I can say just a little bit about
3 days.
a little bit of the ASD paleo weather project that we're starting. It'll wait until Duratio comes, which is not until this fall. It's our new supercomputer. And it's been held up, I think, by a lot of the other issues with supply chain. But basically, the computing group, whenever they get a new supercomputer, asks for proposals both from the university and from NCAR that can run some exciting new simulations in 2 months. So these simulations have to start whenever Duratio gets released to us and be finished in 2 months. And so for those of you who don't know me, my background is actually meteorology way back. I'm not a geologist. And thinking about weather, and especially extremes like tropical cyclones, atmospheric rivers, frontal precipitation, is all very exciting. Also, the fact that many of our proxy records, we really should be, as was shown in previous talks, really get at high resolution for topography. And so we put one in, and it's truly a community effort. It takes advantage of some of us at NCAR and our collaborators at University of Arizona and Connecticut to really put this together and make it convincing. NCAR's into actionable science. So for these, they're expensive. 50 years costs 10 million Duratio core hours per simulation. So we're able to put in for 4. Of course, we'd love to do even more if we can ever find the time. We put in to redo, they're all going to include isotopes, and thanks to the hard work of Jean and Jesse on implementing isotopes into this high-res version. And I should mention the high-res version, we chose this partly at CESM 1.2 or 3, whichever you like, because that's a really good model, as you've seen for paleo. But also there was a group consortium that did a pre-industrial and future scenario simulations with this version. So we have those already as a baseline. It's called IHESP, the project, which just recently ended, unfortunately. But so we said we have to rerun the pre-industrial with isotopes, but then kind of a low, medium, and high CO2. So LGM, mid-Pliocene warm period, and early Eocene simulations. And of course, these will be released to the community. There's going to be such a resource, we hope. But as I said, I'd love to see more. I know we discussed doing a mid-Holocene. I think it'd be really cool to do a Cretaceous where there was a seaway coming up through Colorado. Key to all of them is, as I think Paul commented yesterday or the day before, it's expensive to spin up a high res. So our simulations are all starting from a very long spin-ups with the low resolution version of this model, either FV2 by 1 or FV1 by 1. So that's kind of key. We can't start a time period where we don't have that, but I think it'd be great if we can get enough time in the future, and if there's interest in the community to set up some collaborations among all of us to come up with some other time periods.
Mm-hmm. John?
I want to echo what Betty has said. I remember at the P2C2 workshop in the summer, one of the time periods that people think is understudied or lack of simulation is Miocene. So I'm wondering whether people are interested, and perhaps a question for Betty, how to really move forward. For example, can we allocate some computer time for this Miocene if people are interested?
You know, I don't even know how much, maybe ESTHER has an idea how much duration time would be available. You know, I think, yeah, I should have mentioned Miocene, and I know there's Cretaceous, like Paul mentioned the Cenomanian, where they've done low res, but I don't know if you can get, I don't know if they're going to allocate us that much time, but we should consider it, or, you know, some other way.
I know that, well, Jesse probably might be able to say better than me, but our original allocation for year 2 was basically double because of the arrival of derecho was supposed to have occurred over that year 2. So they're expecting more cores, and I assume our allocation will go up as a result of that. But I don't know if there's a benchmark yet on derecho for running our simulation, or CESM or CESM2. Yeah.
I mean, we should know before the June meeting. We came up with a benchmark because we had to for the proposal. But we'll be able to run on the test machine GUST, G-U-S-T, derechos of wind events, those GUST, starting probably in about April, and work with the software engineers to make sure we're load balance and all that. So we may have a better idea by the June workshop what's feasible or not. And we can brainstorm then too on if we can get more computer time other ways also. And at that point, I think we'll also maybe send out a survey to this group to make sure we're saving as much as we can realistically that the community might want. Of course, to do extremes, we're already planning on doing some 3-hourly, hourly, 6-hourly, daily of select fields because you have to, but we want to make sure we don't forget anything. So we'll send out a survey to you before sometime in the next 6 months, maybe sooner, hopefully.
I think,
yeah. Go ahead.
I think one important thing is also to have longer run of the pre-industrial, because if you're changing the boundary condition, the carbon cycle needs to have a long adjustment time, unless you come up with alternative methods, and often the physics may be spun up after 1,000 years, but not the carbon cycle. And so I think that could benefit larger portion of the community to have a longer spin-up reference runs. Then typically I would guess the other working groups are not interested in these long pre-industrial runs. And I see some benefit if you run it with carbon cycle.
I know the standard CESM2 pre-industrial is now 2,000 years long.
Yeah.
And it doesn't have carbon isotopes, but it does have the carbon cycle.
Okay,
there.
so that's already good timing.
Yeah, that's already there. And I can't recall, the IHES pre-industrial is only 500 years, but it is pre-industrial, and they started from I think from the spun up model.
Yeah, but 500 are not enough. Yeah, you need to run with longer. Yeah.
Well, I think they started from a run that was spun up already, so that's how they, maybe at lower resolution. So
another interesting thing is in terms of the carbon cycle, it's hit the model hard.
Yeah.
Because it may cause a lot of problems. So if you're running under high CO2s, even with present day geography to test it out, it is also working under more extreme conditions. Yeah.
Well, and on the other end, I think Esther mentioned it. I think we really need to promote more efficient, faster, lower resolution versions as we move forward to CESM3, because you do need those for a lot of, in fact, even the simulations we're running as part of this ASD are all starting from very long, low resolution runs so that the ocean has had time to spin up. So yeah, we need both, I think, in our community.
And we're not the only working group who makes use of that low resolution fast model. So the land ice working group mentioned they wanted to retain that functionality, and biogeochemistry working group as well. So yeah. Well,
I'll make one other point, Esther.
Sure.
I think you did already, but it's kind of important, and it was obvious when Greta was talking, is we have our wish list. We want dynamic veg, we want SLIM, we want ice sheets, we carbon isotopes, water isotopes, but that really means we should get involved in the development working groups, the land model working group, if that's your interest, dynamic veg or SLIM, or the land ice working group, because that's where a lot of the decisions are made on development. So I was really excited to see Greta's talk, where she's talked to CLM, she knows its challenges for what she's doing in SLIM, and I think that's really key. Is they're all interested in paleoclimate, all the working groups, but they have a lot of other things they need to work on too. So get involved in those working groups in addition to this one.
Well, and I think it's important to keep a configurability for paleo and alternate Earth capability, because some of the modeling groups tend to, all the input data sets are based on modern data sets, like the land surface data set. When you set it up, it uses a lot of modern data sets to do those PFTs and the soil color and the soil texture and things like that. So being able to have take out the anthropogenic influence from a setup is really important, not to keep that ability for paleoclimate. And Elizabeth just put in a link for the polar and land ice working group meetings that are coming up in the first half of March. So check that link out there if you're interested. And maybe Jean wants to end our discussion, and unless anybody else has anything to contribute, but maybe Jean could remind us about the pause. So Paleoclimate webinar. It's coming up at 2 p.m.
Yeah, so we have 20 minutes to go. Welcome everyone. Please join the Paleoclimate Advances webinar series. And in case you haven't noticed, we will use the same Zoom link. feel free to stay if you like.
I'll probably stay on.
Okay.
And I guess Esther can say the last words, but in case she hangs us all up, this has been a great working group meeting. Such interesting talks. I'm going to go back and watch them all again on YouTube. But I really want to thank Esther and John and Arnie for putting this all together, and then all of you to participate and give your talks. And it's a great diversity of what we're doing and thinking about what we could do. So I'm going to clap, and Christine's clapping too.
Yeah, I thought it was really great. I was really happy to see an incredible new data set and a new way to look at data with the South American Uri's data and Tyler's patch and an alternative Earth type snowball Earth modeling work being done, but just all of the work, the work we had this morning with the meltwater events was really interesting. So yeah, thank you all for your contributions, and I hope you stay involved. Like I said, we're heading into a new cycle where we will be writing another CSL proposal. So if you have good ideas, please stay in touch and be involved. So anything else, Arnie?
No. I think it was a productive meeting, really interesting talks, and hope to see you in the summer.
Yeah.
And at the pause.
Great. All right. Thank you. And I'm going to stay on. I'm just going to disappear for a while, but